All right, good morning. This is Stump the Instructor week. Question and answer. So I was actually thinking about, I was talking to Sebastian about it. Nobody comes to these classes. I don't know why. This is a very small group that comes to this particular class, question and answer, which is unusual. Seems odd to me because
Did they see anything?
you can ask me anything you want, and you've already paid for it, and there's no $75 an hour, and you get 3 hours of this. So anyway, but for whatever reason, I guess people don't want to come. I was thinking maybe we change the name of it to Stump the Instructor, and then if anybody stumps me, you get something. You get like 0.5 aircraft rental or something like that. But I don't know if I want to do that. Then you guys might stump me. Might come up with something to stump me. All right, so I have not prepared anything. Sometimes I do, sometimes I don't. I didn't prepare anything, so hopefully we got a lot of questions that I can answer, and those will lead into other places. So, did everyone bring Did you know it was Ask the Instructor Week?
No, but I can.
You got some? Okay. All right, so then I think everybody has some questions. So who wants to go first?
I'll start.
Go ahead.
Just to understand these planes that we fly.
Yeah.
Because of something that happened to me recently.
Okay.
What if I'm out flying around out here?
Okay.
I might be at 3,000 feet practicing.
All right.
And 10 miles from the airport, engine goes out.
Okay. You're going to land.
Why do I have to land in a field if I can glide it?
If you can get it back to here, then you don't have to land in a field.
Yeah.
The question is, can you get it back to here?
That's just it. It's just not minimum glide ratios. If you're at a certain height.
Yeah,
you'll
so
be
that's
able
for
to
the
glide
that's
so
for
many
the
miles.
GX.
Uh-huh.
So flight level. So the glide ratio. Get my glasses here. And then, well, I'll tell you.
You can use
That's
it.
okay. I know what they are.
It's page 37.
Yeah, I know what they are. Essentially, in the GX, what the book says is about 12 to 1.
Uh-huh.
And in the G3, the book says 17 to 1. Okay. That would be if that's a no wind scenario, okay, no wind. And that's if you are flying the airplane, if your piloting skills are perfect, okay? So more realistic of what you can think for the GX, for the GX is, let's say, 10 to 1.
Uh-huh.
And for the G3, think 15 to 1. Okay, now what does that mean? That means for every 1 foot of altitude loss, you go forward by either 10 feet or 15 feet. That's what that means. So if you are at 5,000 feet, or let's just say 1 nautical mile or statute mile, whichever, if you want to use an apple or an orange, if you are 1 mile above the ground, not sea level, but above the ground, okay, then if you're in a G3 and you do everything perfect and there's no wind, you can glide 15 miles. If you're in the GX, you can glide 10 miles. That's what the glide ratio communicates. Now, you got a wind plays into that. You got a headwind, you're not going to go as far. You got a tailwind, you go a little bit farther, right? So you have to be judging that as you're flying constantly. You're constantly recognizing, hey, where can I go from here? Where can I go from here? And you don't want, let's say that you know that your glide distance is 10 miles. Well, hopefully your field isn't 10 miles away. Hopefully you got a field that's 5 or 6 miles away, and you've got a little excess altitude to work with once you get there. Okay, does that help or make sense at all?
I'm just wanting to understand. That is what it really means.
That's what it means.
Still, no wind.
No wind, correct.
You could go a long way.
That's correct.
From 5,000 feet.
That's correct. So, and the other thing, the other way to look at it when we start talking about the winds in it, look at it this way. Let's assume that if you're at your best glide, which by the way, best glide is going to mean flaps are up. And if you have a retractable gear, the gear is sucked up. You want to be in the cleanest configuration you can from a drag standpoint. You want to be as clean as possible. And you want to be flying at the speed that will be the most efficient from a drag standpoint, right? So that is V glide, okay, velocity glide. All right, now where do we find that on the airspeed indicator? Is it shown? Is it indicated on the airspeed indicator? Best glide?
Not really.
No. Is there an airspeed that's close to it?
Yeah, VY.
VY. VY is very, very close to it, okay? And why is that the best glide speed from a drag standpoint? Do we remember that? We talked about that real quick. Might as well put a little meat on that bone. All right, so here's your speed axis.
It's like the most efficient state between the drags.
That is exactly correct. So you've got the two drags, speed 0 here. If we're not moving, we have 0 drag on the aircraft. As soon as we begin moving, drag increases, and the faster we go, the more the parasite drag becomes. Parasite drag, you need to put your hand out the window, the faster you go, the more drag you feel. Then we have the second type of drag on an aircraft, which is induced drag. And induced drag it's induced by the production of lift. So at what minimum speed could the airplane fly, let's say, in the clean configuration? In other words, the flaps are not retracted, the flaps are not down. We call that VS1. What speed is that in these airplanes? 50, about 50. All right, so we got to come over here to wherever 50 lies on the speed range, okay? And at 50, we start producing induced drag, and it's very, very high, okay? The slower we're going, the higher the induced drag, and then as we speed up, it dissipates off, right? So this point right here, that's the best spot right there. So that speed right there, whatever that V speed is, that's our best glide. That also happens to correspond closely, not exactly, but very closely with VY. Okay, so when we're flying that speed, assuming we're keeping drag to a minimum, and by that, that means the flaps are retracted, the gear is sucked up, we're as clean as possible, that will be the speed that will reduce drag. Any faster, and if this is our total drag, if you take these two curves and you combine them, you get a total drag curve that's going to look, something like that. So any faster, and this should be right at the bottom of the total drag right there. So any faster, and drag begins to increase. Any slower, drag begins to increase. So if we want to glide as far as we can glide, we need to reduce drag. That's the only answer. We have to reduce drag to glide as far as possible. Now the way winds play into that is, let's say that at best glide you have a descent rate of 500 feet per minute. Let's just assume it's 500 feet per minute. It'll be whatever it is, okay? Well, at 500 feet per minute, let's say we're at 1,000 feet, all right, and we're flying at best glide, and there's no wind, okay? Well, at 1,000 feet, if we're in let's say the G3, and we're descending at best glide, let's call it 70, indicated, all right? How far will we go? In the G3, we'll go 15,000 feet, right? If we have a 15:1 ratio, and the GX would be go 10,000 feet, if there's no wind, all right? So this would be 15,000 feet in the G3, in theory, according to the manufacturer. Does that make sense? That's how far we would go. And we would do it we would descend, we'd hit the ground 2 minutes later, because we're descending at 500 feet per minute. So in 2 minutes, we would go that far and we'd hit the ground. Well, what if the wind were blowing in our face at 70? At 70. We'd still hit the ground in 2 minutes, but we'd hit the ground right here. All right? And if we had the wind blowing at us like that at 70, we'd still hit the ground in 2 minutes, but we'd hit the ground way down here. Does that make sense? Okay, so that's how wind plays in. Time, descent rate won't change. If you're descending at 500 feet per minute and you're 1,000 feet above the ground, you're going to hit the ground in 2 minutes. Where you hit the ground depends on the wind. Right. Okay, and if there's no wind, you'll hit the ground, in theory, at whatever the glide ratio. 10-1, 15-1. If you're in a high-performance glider, 70-1. It depends on the glide ratio of the airplane. And the glide ratio is heavily dependent on the wing loading. The lighter the wing loading, the better the glide ratio. And other things. It can depend on wing design as well. The longer the span, in other words, the higher the aspect ratio, the ratio between the span and the chord of the wing, the bigger that number, the lower this drag, the lower the induced drag. It doesn't change this one. but it changes this one, which has the effect of taking your total drag curve and making it look more like this. Which increases your glide ratios. Okay,
Makes sense.
does that help?
Yes, yes.
Okay. Anybody have any follow-up questions related to what we're talking about here that ties into this in any way?
You, instead of like gliding down.
Yep.
If you tip the nose down, gain a lot of speed.
Yep.
And then like pull up slightly so that would that work?
No, you wouldn't go as far. What would happen is as you go faster, your drag increases. Okay, so you have, we're talking about energy is what we're talking about. And when we talk about energy, as it relates to an airplane, there's four things that we talk about. We have potential, which is the altitude. We have kinetic, which is the speed. We have chemical or fuel. If the engine's running, we can add power. And then the fourth kind of energy that we don't really talk about much is air mass energy. In other words, drag. We lose some of our total energy from drag, okay? So for the same reason that if you take, this is interesting, we were talking about this yesterday in our instructor meeting, as a matter of fact. If you get on a roller coaster, you've been on a roller coaster, right? All right, so you get on a roller coaster, and that roller coaster, you know, it goes up the hill, and then you get to the top, and then you free fall down, and then you usually go up another hill. But guess what? The other hill is never quite as high as the first hill. You ever notice that? It's never quite as high. It can't be as high because of this thing with energy, this process of conservation of energy. Okay, so you have a certain amount of energy, and you can't add energy to it unless you put fuel to it. You can add energy if you add chemical energy, but the potential, and then we turn that into speed, and then we turn that back into potential. But we can never get the same amount of potential because we lost some of it in air mass and drag. So as we lost some of it in drag, we don't have all of it to get back up to where we were at. And so for the same reason, when you dive the airplane, you increase a lot of drag, which means you dissipate a lot of the energy reserve that you had just by heating up the air. This drag, you heat it up the air, and now you can't do as much with it once you pull it back out. Does that make sense?
Yeah.
Okay. Once you have energy, you can't destroy it or add to it. Energy is energy is energy, and you can move it over here, but you can't add to it. Make sense? All right. So that's the reason that in a glide, if you want to maximize, regardless of wind, if you want to maximize your distance, you need to fly at that speed right there. Because any faster than that speed, then drag begins to go up. Any slower, drag begins to go up. And you're turning what energy you do have into heating the air, which does you no good, right? We don't need to heat the air. We need the energy distance, right? Okay. Anything else on this before we get to the next question? All right. All right. You haven't stumped me yet. One down. All right, what's next?
So AGL versus MSL,
Uh-huh.
like a quick breakdown between the two, and wider pattern altitudes always in MSL than AGL.
Okay.
That's kind of a
MSL versus AGL. Why what? MSL versus, why do we have two of them?
Well, sure.
What are they?
But like, whenever you look at it in the pattern,
Mhm.
like when you're looking at what it is, it's always in MSL
Okay.
rather than AGL. So what's the purpose? Why?
Okay, why charted in MSL? Is that kind of what you're
Yeah.
asking? Why do we chart it in MSL?
Yeah.
Okay.
And so when it is in MSL, when you're looking at it, is there a quick conversion for AGL? Like if you're
No.
flying the aircraft?
No,
Like,
there's
how
not.
do you-
So if you don't have
How
it,
are you confident that you're at the right level when you enter a pattern?
okay. So you need first of all, the regs specify that we need to, before we take a flight, we need to what? Before we go on any flight, you're getting ready for your stage 3, you know the answer to this. We need to be what?
Like aware of all the information available.
Yep, all the information available about that flight, which includes whatever airports of intended use.
Arrivals.
Yep, so if you intend on using some particular airport, you're gonna know what the field elevation of that airport is. You're gonna know how high the airport is above sea level. And then you just simply add 1,000 feet to that and you've got pattern altitude, okay? So, and the reason that we chart things in MSL is really simple. We want a benchmark, if you will, that we're all flying to. We're all flying at the same benchmark, and that benchmark is sea level, height above sea level. We can't really use height above ground level because you'd be constantly changing your altimeter because the ground is doing this, and you can't fly and just change the altimeter all the time. And we don't have radar altimeter in our planes. We don't have radar altimeters. You know, if you had a radar altimeter, then you'd know the altimeter would be doing this as you go, you know, fly across the ground. So we don't. We have barometric altimeter. So the barometric altimeter is set to the barometric pressure at sea level. In theory, whatever sea level is directly below us, that's what we set the little Colesman window, the little knob to set the barometric pressure to whatever the pressure is supposed to be. And I use the air quotes here because it might be, it might not be, but it may not, if you actually, you know, were able to dig a hole and get down to sea level and put a barometer down there and read it, it may or may not be what they're reporting it to be. But everyone around you is setting it to the same thing. So we're all flying at the same pressure level. Okay, that makes sense? All right. So we need to all be flying to the same pressure. Everyone that's close to each other needs to be flying at the same pressure level so that even if the pressure level's doing this, we're all we're all doing the same thing together on the pressure level. Does that make sense?
Yeah.
Okay.
So that's only pressure level is going to be changing.
Pressure level absolutely will be changing, okay? So that's why when we're flying cross country, what are we doing? This is part of your state. I'm just doing part of it right now since I know we're getting ready to do it. What are we doing?
Changing the altimeter.
As we go. So as we go, we're listening to airports that are either right along our route or close to our route. We're listening to the AWAS, ASOS, ATIS, whatever they have available. And we're listening primarily, I mean, we're listening to everything on there because all of it's important, but there's two pieces of information for us flying across the country here that are really important. Really.
That's the pressure. Wow.
Pressure altitude, or not pressure altitude, the pressure, the sea level pressure is really important because we're going to adjust our altimeter so that we're flying at the right pressure level, right? And what's the other thing that's important? We were just kind of talking about it. Wind. We want to know what the surface winds are because if we do have that engine failure and we got to glide to a field someplace, we want to know whether we want to land in this direction or that direction or that direction because we want to know what the surface winds are. So those two pieces of information, when you listen to AWAS, ASOS, ATIS, even if you're not going into that airport, the altimeter setting, so you can change your altimeter as you fly, and the surface winds are really important because if your emergency happens right there, you and I already know kind of what direction you're going to want to be landing in. Okay?
I would add one more thing.
Sure, go ahead.
Is information, especially in our area, or if you're going east, and that's temperature and dew point.
Oh, sure, yeah, temperature and dew point, absolutely, that's important. Why is that important? Thank you. Why is that important?
About fog, yeah.
Yeah, the closer they get, yeah. And so it could be fog, but it's also just in general, as if you're flying someplace, and it's not so much when we're flying around here, you know, we're flying 50 or 100 miles, but if you're going, you know, you're going from here to Miami or something, and you're going around, you know, Tim's house down there, Louisiana, where's that, Louisiana? Yeah. You're gonna go, you're not gonna go across the Gulf, you're gonna go that way and then down to Miami, right? So when you're doing that, as you're listening to ATIS along the way, if the altimeter setting is dropping, then it drops by a couple of, you know, a hundredth, and it drops another hundredth, dropping. What that's telling you is that I'm flying towards bad weather, potentially bad weather. because we associate low pressure systems with bad weather. Why? Because a low pressure system, remember in the weather class, we talk about, I use the analogy of your bathtub, right? And so here's your bathtub, right? Down here is the drain. That's the lowest part of the bathtub. So when you take a shower, take a bath or whatever, and you're out working in the fields and you're dirty and and the water's just filthy, where's all that bad, filthy water go? Right? So high pressure forces whatever is bad in the atmosphere towards the low, right towards it, pushes it right into the drain. So if you're heading towards low pressure, you're heading potentially, doesn't mean there will be bad weather, but potentially the weather could be getting worse.
You at least need to be aware.
Be aware of it. You could be flying into an area, if you're flying into low pressure, you're flying potentially into bad weather. And the reverse is true. If the weather's, the pressure getting higher, better and better, you're flying into better weather.
And isn't there a mnemonic you had about if you're from high pressure?
High to low, yeah. So high to low or hot to cold, look out below. So we use that when in reference to the altimeter setting. Use that in reference to true altitude versus indicated altitude. So our indicated altitude is whatever we say. So let's say here, let's say this is sea level. Here's sea level. What's the field elevation of this airport? 650. All right. So let's say this is 1,000 feet right here, 2,000 feet. Okay. So let's say 650 is, I don't know, right here somewhere. Here's 650 feet. Okay. And here's sea level down here. And let's say that the altimeter setting, well, what is it today? Somebody look it up. We'll just use a real example. What's the altimeter setting here right now?
$30.01.
30.01. Okay. Is that a high pressure or a low pressure? From standard.
Slightly high.
That's slightly high. It's a little bit higher. Okay. 30.01. So the pressure at sea level is 30.01. Okay. So our altimeter, and I don't want to lose track of what I'm talking about. I'm already starting to lose my train here. What was the question that I'm answering?
It's hot to cold. High to low.
High to low, hot to cold. Okay, thank you. Well, I was losing track of what I was talking about. All right, so if this is the sea level pressure right here, and we're sitting in our airplane right up here, or we're just standing here with an altimeter in our hands, all right? The altimeter is a barometer, that's all it is. Think of an altimeter as a tape measure. It measures a distance, and it measures a vertical distance, okay? So what you want to do with your tape measure, if you want to measure, if you're standing up on a ladder and you want to measure how high you are, or if you take your tape measure, you want to measure how high that is off the ground, what are you going to do? You're going to drop the end of that tape measure until it touches the ground, then you're going to read what it says, right? That's what we do with an altimeter. What we do with the altimeter when we change that little knob is we say, okay, drop that the end of the end of the tape measure down to sea level, and now let me read what it says. That's all we're doing. So what we do with the altimeter today is we get here, we hold the altimeter, and we put it to 30.01. We're dropping that down to what sea level pressure is, and we're reading the altimeter, and the altimeter should say 650 feet. It should show that we're 650 feet above sea level. Okay? And then if we took off from here, we set it to that, if we take off from here, and we climb up to 2,000 feet, it should read 2,000 feet, because we still have the end of it anchored down at sea level. As long as we keep 30.01, it's anchored at sea level. And as we go up and down, we're just taking our tape measure and moving our tape measure up and down. That's what we're doing. That's what our altimeter is doing. Does that make sense so far? Okay. All right. What happens, however, if we start flying along here at 2,000 feet, okay, and our altimeter is set to 30.01, all right, 30.01. But let's say that as we move along on a cross country someplace, the sea level pressure down here, instead of being 30.01, goes to 29. 29.0 or something like that. Well, what's happening is 30.01 now is actually up over here. It's coming up like this, so it's higher, or excuse me, the other way around, sorry. It's lower because higher pressure would be lower. The lower you go, the more pressure there would be, right? Okay, so what are we going to do in our airplane? If we keep it at 30.01, we're simply going to fly a pressure level, and we're going to do this. We're maintaining 2,000 feet above wherever we set, wherever 30.01 is. So what we're telling our tape measure is to go down to where the pressure level is 30.01. Okay, so as we fly along, the pressure at sea level changes. So we have to constantly be adjusting the end of our tape measure so that we maintain 2,000 feet. So high to low, so here we're flying from an area of a sea level pressure of high pressure to a sea level pressure of low pressure. Look out below. We're flying downhill. So that's where the high to low, look out below comes from. And the same thing with hot to cold. So hot to cold will have the same effect. You'll end up flying downhill. Okay? Capiche? All right. Any questions on this? Want to go deeper into this anywhere? Okay. All right. Good question so far. Still waiting on the stumper.
I don't know, do we really want to stump you?
Yeah, I want you to. I really do. If you can stump me, I'll come back next week with the answer. I don't know everything. I really don't. And yeah.
Talk about stable versus unstable air.
Stable versus unstable air. All right. So the way that when you read it in the book, what they talk about is a parcel of air. You take a parcel of air, and take a little bubble of air, if you will, and what does it do as it goes up in the atmosphere? Does it go up and kind of stop where it'll rise if it's hotter than the surrounding air? Or if it's less dense than the surrounding air, it's going to rise to the point where the density equalizes and it's going to stop right there. Okay. The stability or instability of the air kind of depends on what happens to that parcel. Does it not rise as far as it would maybe normally rise in a standard atmosphere? Does it go where it would normally go, or does it go even higher? Okay, so the way I like to talk about it is by looking at the standard. You have to, first of all, we have to be familiar with the standard atmosphere, right? So everybody in this room is familiar with the standard atmosphere, correct? Okay, what is it? Okay, what's the temperature?
15 Celsius.
Okay, and what's the lapse rate?
1 degree Celsius per 1,000 feet.
No,
What?
2 degrees Celsius.
What? Okay.
Temperature's 2 degrees. Pressure is 1 inch. 1 inch, okay. All right, so the sea level, standard sea level pressure is 29.92 and the temperature is 15 degrees Celsius or 59 degrees Fahrenheit. Standard, which never happens, right? We're all aware that this never in the real world doesn't really happen. It's just something that we use as a starting point, excuse me, a benchmark. And then we have a change in both the temperature and the pressure as we go up, so we call that the lapse rate. How much does the temperature and the change lapse as we go up? Pressure will decrease and temperature will decrease as we go up. And it decreases by 2 degrees Celsius or 1 inch of pressure. All right, so then in that case, let's take a slice of the atmosphere. Here's 1,000 feet, or let's call that sea level, 1,000, 2,000, 3,000, 4, 5, 6, 7, 8, 9, 10. Okay, so sea level, go over here. Sea level 1, 2, 3, 4, 6, 7, 8, 9, 10. So in the standard atmosphere, so I'll use black for the standard, in the standard atmosphere, what should the pressure approximately and temperature approximately be at 10,000 feet? Approximately. Remember, it's an approximate 1 inch. It drops by an inch per 1,000 feet, so
20 degrees.
about 1992, something like that, right? So this is 29.92. Therefore, when we get up here, it should be about 19.92. Now, this doesn't mean that you get up there and set your altimeter 19.92. Your altimeter is set to sea level and it's reading, okay, you're 10,000 feet above that. But if you had an actual barometer that's measuring pressure up there in the airplane with you, it's a standard day. It should read 19.92 inches of pressure or something like that. Okay. What should the temperature be up there? Down here, it's 10. It's 15C. What should it be up there? That's decreasing.
25.
No, it's decreasing.
Yeah, minus 25.
Minus 5.
Okay,
Yeah, 2 degrees Celsius, right? So minus 5. All right, so we should have minus 5 degrees C. So that would be standard. If we got up there and we had this, we would have, at least at 10,000 feet, we would have a standard atmosphere. And if everything lapsed at that perfect rate going up, we would have a standard lapse rate, right? Everything would be good. But what happens if we get up here to 10,000 feet? What do you think this parcel of air would do? Let's say it got this high. Let's say it was able to get this high and it gets up here to 10,000 feet. And when it reaches 10,000 feet, rather than the pressure being 29.92, the pressure is 25. What do you think that partial of air is going to do? You think it's going to keep going? Nope. It's capped. It isn't going any higher. What if it gets up there and the pressure is 15? It's going to keep going. All right. So when you have pressures lower than they should be and temperatures higher than they should be, then you're going to have an atmosphere that's kind of unstable, right? It's going to allow a parcel of air that's already rising to continue. It wouldn't normally stop where it should stop. It's just going to keep on going because the atmospheric conditions are not such that it's saying, okay, no, you need to stop right here. No, you can come on up. Does that make sense?
Yeah, and it's just based on what is it, 4.4 per thousand feet?
That's the adiabatic lapse rate. So that's how you calculate the cloud
Cloud
basis.
basis.
Yeah.
But I mean,
Yes,
some way
that's
you could
there.
use that in this,
Yeah, you could, and if Joseph Hill was here, he could probably give you the formula for it. I don't. I'm certainly not a meteorologist, but this is the easiest way for me to think through how to talk about a stable or unstable atmosphere. I just use the standard atmosphere, right? So if we have pressures and/or temperatures that are going to promote a parcel of air going further than it normally would, I have an unstable condition. If I have temperatures and/or pressures that are going to stop it, or even keep it from going higher than it normally would, I have a very stable atmosphere. Does that make sense?
Right.
Yeah. Okay. Yeah. All right. So while I'm here, because it's a good place to bring in thunderstorms. Let's bring thunderstorms. So what do we need for a thunderstorm? We need 3 things. There's 3 ingredients.
unstable air.
Unstable air. This is it. Unstable atmosphere. This is your unstable atmosphere. And then you need moisture, and you need one more component. Lifting source. You need something taking that parcel of air and tossing it up there. So you could be stable down here, somewhat stable or normal, okay, such that parcel of air is kind of stopped right where it would normally, but it's unstable up here, but it's kind of stopped right here, but then you take another force and you say, oh, well, just kind of, let me tap you up a little bit. Oh, now it gets going. So you got to have something to take that parcel and say, okay, let me volley that up. You know, you play volleyball, just let me get that up there. So you got something lifting it, and then you have an atmosphere that just lets it go. And then you have moisture, and then you have a thunderstorm. Or you could have a thunderstorm. Okay. That's good questions. Don't be shy.
Can you go over, I think I know, but I'd like you to see how you would write it up here and maybe solidify it in my mind.
Okay.
Skidding versus slipping.
Skidding versus slipping. All right. Well, yes. Let me talk about it before I draw anything up there. Everyone is familiar with skidding. Everybody knows what skidding is. Just like everybody knows what parasite drag is. You drive down the road, you put your hand out the car, and the faster you go, the more you feel that's parasite drag. Skidding is the same thing. If you're driving down the road and you're not on a racetrack that has banked turns, you're driving down the road and you make a left turn or a right turn, where does your body go? Does your body fall to the inside of the turn? No, it gets thrown to the outside of the turn. That's a skid. That's a skid. When you get thrown to the outside of the direction that you're going, you're skidding. When your torso, oh, this is turning red. This is getting ready to die. When you're making a turn, if your torso or your body feels like you're getting thrown to the outside of that turn, you're skidding. If your body or your torso feels like you're falling to the inside of the turn, you're slipping. Okay? So when you're looking at the ball, let's say in this case, we're turning that way. And here's our ball, okay? And we could also have the ball right in the middle, which means we are coordinated. In other words, your torso doesn't feel like you're slipping or skidding. You are perfectly coordinated in your turn, okay? But if while we're turning that way, the ball is out here, are you slipping or skidding? You're skidding. You're being thrown the ball, or your torso is getting thrown to the outside of the turn, just like you'd feel in a car. If the ball's over here, you're slipping. You're falling inside the turn, okay? So you can use the ball, and a lot of instructors teach to use the ball. I really try not to teach to use the ball other than to reference it in reference to feeling your torso. Feel your torso. Your torso is going to do the same thing the ball is doing. If I'm in this airplane and my torso feels like I'm straight up and down, I'm not slipping or skidding. We're turning this way. If my torso is falling to the inside of the turn, we're slipping through the turn. If my torso is thrown to the outside, we're skidding through the turn. So I don't really use the ball. I feel it in my torso. And that's one less thing I got to look at, okay? And the quicker you begin to recognize that and start to try and feel that kind of seat of the pants thing, the better you're going to fly the airplane, all right? And now the question is, what do you do? What's your instructor tell you to do if you see this? Yeah, step on the ball. Step on the ball, right? So you're using the rudder in the direction of the ball. It's the same thing with your torso. If you're falling this, if I'm walking and I'm falling this way, I'm not going to try and prop myself up with that leg. If I'm falling this way, I'm going to use this leg and prop myself up. If I'm falling this way, I'm going to use this leg, prop myself up. So if you feel like you're going this way, you need that side. If you feel like you're going this way, you need that side. And then it's not looking at a ball. You just, where's my body going? Let me stop that. Let me stop that.
Now, how does this compare to a forward slip?
A forward slip?
Right.
You'll fall. Your body should be falling inside. You should be.
So
if you're
it's
banking
kind of
this,
phenomenal.
it's a slip. Yeah, you'll be falling into it. If your wings are like this, if you're in a slip and your wings are like this, you better be falling into it.
Okay.
If your wings are like this, you better be falling into it. If you're slipping, you're falling into the direction of the turn. If you're not, you better stop what you're doing. Okay? So there are absolutely times when you're flying an airplane where you're going to slip the airplane. It's a maneuver that we use. It's a maneuver that every pilot needs to know how to do. Okay? Slipping is not, provided you maintain energy, which is true with anything in flying, right? Slipping is not a dangerous maneuver providing you're maintaining energy. Just like flying straight and level is not a dangerous maneuver providing you maintain energy. You don't want to stall while you're in the slip any more than you want to stall when you're straight and level, right? So you have to maintain energy. Skidding is never good. Never good. You never want to feel your body going to the outside of the turn, ever, unless you're doing aerobatics or something, which nobody in here is doing, right? At least not right now. Does that
Yes.
help? Okay. So I would, if I were you as you fly, I'm not saying don't look at the ball, but if you look at the ball, I want you to also relax your torso and recognize, oh, the ball's over there, and you know what? I feel my torso over there too. I feel like I'm sitting straight up now, or whatever. And then you will begin to develop that seat of the pants feeling much, much quicker in your flying career. And the faster you develop that, the better pilot, better you'll fly the airplane all the time. That's just one of those things.
That helps a lot.
All right. And to look at it from an airplane standpoint, just so I throw that in there, it's a function of where's the tail with respect to the nose. So this would be a coordinated turn, and if you look at the line that's being drawn between the nose and the tail, look at the flight path, and you can see that the flight path of the nose, the nose and the tail are both traveling through the same line. Okay. What about now? We're slipping. The tail is falling to the inside of the turn. Skidding. The tail is being pushed or thrown to the outside of the turn.
What's the danger of nothing that skid like?
So the danger of the skid, especially if you get slow now, is because let's look through the stall. So it's a skidding stall spin accident. So what happens is if you're turning, let's say skidding through a turn, okay, and you get slow, you're skidding through a turn. One wing is retreating and one wing is advancing. Which wing is retreating? This one down here, right? So which one would stall first?
That one.
And in that turn, you just roll over. And it's a quick, rapid rollover. And when that happens on base to final or downwind to base or low to the ground, downwind to base shouldn't be an issue. Well, you shouldn't be skidding through it anyway. But it's the base to final one that kills you because you're so low to the ground, there's just no recovery, right? But if you were slipping, let's say you're slipping, coming in and slipping, or you're slipping through a turn, okay? Even slipping through a turn, if you got slow, which wing is going to stall first? This one over here. So the stall will be this, up over the top. The stalled wing will drop. Have you done turning stalls? Which wing drops? The high wing, right? So when you're slipping like this through a turn, the high wing is going to stall in that case, and this wing, and the stall, the recognition of a stall is that this wing comes up. Now you can get that nose down and recover from that scenario versus this where you just roll over. Okay?
That's helpful.
Okay, but either way, even when you're in a slip, you still need to keep your energy, right? Forward slip or side. The slip where you're not keeping energy is the side slip where you're doing a crosswind landing. Now the intent is to bleed the energy until the landing occurs, but you're doing in a cross-controlled situation. All right, good.
Since nobody's asking.
Yeah, ask away.
We are in VOR and we're heading to from.
Okay.
To from. And,
Wait, you're heading to or from?
well,
You can't be
I wanna
both.
head to.
Okay, all right.
Okay, I'm flying out here. I might be lost.
You might be what?
I don't want to be lost.
Okay.
I might be lost.
Okay, so you're trying to find
But
yourself
I
reference to a
find
VOR?
VOR, and I have not even seen it, so why am I asking this question? But I'd like to understand it.
Okay.
If I'm flying to something, I'm supposed to be flying 182. Is that?
Well, 180, forget the number, it depends on what radial you're on. You're either flying to or from.
Okay.
Okay, so picture a bicycle wheel first off. Picture the hub of a bicycle wheel. Here's your bicycle wheel. And let's just picture some spokes on the bicycle wheel. Okay, forget a VOR, just this is a bicycle wheel, all right? And you got this spoke right here, this straight spoke right here. It's collinear with that one, isn't it?
Right.
And this one is collinear. Everybody know what collinear means? Say collinear, collinear. All right. This one is collinear with that one, okay? Right? But they're two different, this is not the same spoke. This and this, although they move in the same direction, are not the same spoke, right? Okay. Let's say that you happen to be on this particular spoke right here, whatever it is, okay? Well, if you're looking at and moving in the direction of the hub, you are flying or moving to the hub. You're flying to the hub. You can be on this particular spoke and flying in this direction, and now you are from the hub, right? So you can't be to and from on the same spoke at the same time. You have to put it in reference. You have to put things in reference. Now, I'm saying, and can be confusing, I'm sitting here saying, all right, well, if you're moving in that direction, you're to it. If you're moving in this direction, you're from it. That's not technically correct when it comes to VOR, because let me just move the hub and that spoke out over here. You can be right here, X marks the spot, okay? And you can be, even if you're moving in that direction, right? You could still be to or from depending on what you're trying to do or how you have your radio set up. Okay? So if you just always think, well, if I'm to, that must mean I'm flying to the station. Well, no, that doesn't mean that. It means you have your radio set up to fly to the station, but you could be flying the opposite direction, right? So that's where some confusion comes in with flying radials. But the basics of VORs are simply that when you're using a VOR, it's a very dumb instrument. There's nothing smart about this instrument. The brains have to come from here. All you can do is say, I want to focus on this hub right here. I want to focus on that hub. So I got to tune in that hub. I got to have some way of setting up my radios to say, look at that hub. And then I have to say, and look at that hub and this particular spoke. I can only look at one hub and one spoke at a time. And then the information that comes back, I have to use my brain for that to tell me, to derive some information from what I'm seeing. Okay, so here's a VOR out here. I can say, okay, I want to look at that VOR and I want to look at that spoke, or we call it the radial. We look at that.
Now, would you say that could possibly be your heading?
Could be, but you could be over here. You know, we're near that spoke.
Right.
But tuning in that, looking at that VOR station or hub, and then further drilling down to this particular spoke or radial will give you, if you understand how this system works, will give you some inclination or information about where you are relative to that hub and that spoke. Okay, so all VOR equipment in the airplane, the navigation equipment, a nav radio in the airplane, all it can do, along with the head, the VOR head, and the station on the ground, all you can do essentially is two things. You can set up your radio. You can do two things. You can tune in a hub or a station, and you look at one of 360 radios, and then it's going to give you some information, and you have to interpret what that information means. Okay, all right. So I just want to say that, and I'm going to go down a little bit deeper in it, but I just want to say that I want you to understand that there's nothing mystical or magical about this. All you can do is say, I want to look at that VOR and I want to look at that radial. And then it's going to give you, it's going to give you information. And then based on what information it gives you, you have to say, okay, well, that means this or that.
Is it giving you or avoiding
Well, it could if you have a thing called a DME, distance measuring equipment. If you have a DME and it's a VOR DME, which puts that information out, then you could get distance, but it's not straight line. It's not ground distance, it's straight line distance. So if you're right on top of the station at 5,000 feet, it's going to tell you you're a mile away, even though you're right on top of it. You know what I'm saying?
Okay.
So the further out you are, the more accurate the DME is going to read. It's because it's just a straight line. Okay. All right, so here's your VOR, and I'm just going to draw 4 radials. There are 360 radials, and they are oriented in magnetic direction. So the 360 radial points towards 360 north, magnetic north, not true north. And this is 090, and this would be 180, this would be 270, and those would be radials off of that VOR, okay? So, and this particular station, it's called an omnidirectional facility. So it's not really sending out 360 signals, it's sending out one omnidirectional signal, and your equipment in the airplane takes and turns that into 360 discrete signals, okay? But You don't need to know that. You just need to understand. You can tune into a station in any one of 360 radios. All right. So in your airplane, you must have a navigation radio. If you don't have a navigation radio, you cannot tune in to a VOR. It's a different set of frequencies. You can't, and you can try this. Go to the comm radio and try and tune in the San Antonio VOR. It doesn't get to that range. You can't even tune it in. So you got to have a navigation radio in order to tune it in, first of all. Okay? You got to have a nav radio. All right? Then you need to have some method of choosing a few things. All right? You need to be able to choose the Omni, OBS, so Omni bearing selector. So this is a method using the Omni bearing selector. What you're doing is you're selecting which one of these 360 omnis or radials or spokes, whatever you want to call them, you want to look at. So with your Omni bearing selector, you have a choice of 1 through 360. You can put one of 360 things in the Omni bearing selector, right? So you're just picking one of those. Then you have to have some type of what I'm going to call a VOR head. Okay, and the head is going to be this thing. For our airplanes, it's this right here. We use the heading indicator as also the VOR head. Okay, but when you look at an airplane, you look at pictures and you see an instrument that looks like this. Usually a circle, usually has a little circle and it has some dots coming out the side. It'll have a line or a needle that moves back and forth. That's the VOR head. Okay, that's what I mean by the head. Okay, and then within the head, you will have a CDI, a course deviation indicator. That's this thing right here. That's the needle. That's your course deviation indicator. Okay, and then you need to have some method of knowing whether you're to or from. That's it. That's all there is, really, in general, to a VOR. Okay, so if I come over here and I say, I'll draw my VOR head right here. All right. And 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. Those dots are, generally speaking, 2 degrees. 2 degrees each. So when you get, if you're 2, 4, 6, 8, 10 or beyond, you have what's called full scale deflection. In other words, you don't know where you're at. Okay? If you have full scale deflection, you don't know where you're at. You can't tell. Okay. All right. And you need to have a to or from. You need to have some method of knowing whether you're to or from. So once you use your navigation radio and you tune in this particular station, let's say we've tuned in that station right there. And let's say that we are located right there. Now notice I'm not drawing a direction, I'm just drawing a position.
Now, are you having some degree of suspicion about where you're at? You know, you're thinking about, well, I think I might be here, but I'm not sure.
Well, I'm going to show you here. I'm going to show you how to do that.
This is the confusing part.
Yeah, so I'm going to show you. So let's assume you don't know where you are. Well, let's do it this way. Let's assume you don't know where you are and you happen to be right there. Let's just say you're right there. Okay? And notice I don't have the airplane pointed in any particular direction. We are located. I mean, the airplane could be pointed and flying in any of these directions. It's just that we're physically, geographically here. And then we tune in this particular station with whatever its frequency is, and then we spin the OBS. Let's say we spin the OBS. We're just basically spinning a knob. Just spinning a knob. As we're spinning that knob, what it's doing is it's running through, it's looking at all of these 360 radials. It's just looking at them. And as it does that, this little CDI, this course deviation indicator is going to be going zing, 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 zing. It's going to be doing this. Okay? If we spin it, and it'll center, it'll come to the center twice. It'll come to the center one time with a to indication, and it'll come to the center one time with a from indication. All right?
Okay.
So let's say we're here. We don't know where we are, but we're right here. And let's say that this happens to be 170 radial. We don't know that, but that's where it happens to be. So that means on this side, it would be the 350 radial. Okay? All right. It's going to center twice. It's going to center one time when we have this set to 170, and when we do, it'll say 2. Then you spin it, it'll center again at 350, or excuse me, this was a from, the 170 was a from. And it'll center again with 350 with a 2. This making sense a little
Yes,
bit?
yes. Now,
Okay.
Now it's making more
Okay.
sense.
So if we center, if we stop the OBS at 350, we'll have a 2 indication, all right? And a centered needle, which tells us we're not on the 350, we're on the 170 headed to the 350.
Now that's making
Does that make sense?
That's making sense,
Okay.
yeah. But you determined that because how you're spinning that selection.
Yeah, remember, there's only 2 things you can do. You can say, look at that VOR, and we do that by putting the correct frequency in the nav radio. And then you can say, look at one of 350 radials, and then you're going to get either a to or a from, and a needle will be someplace. You have to interpret, is it to or from, and where's the needle, and what does that mean? That's where you have to use your brain. All you can do physically is tune in a particular station, look at a particular radial, and then what's that telling me, and what does that mean? Okay? That's how the VOR.
So in a sense, if I'm understanding this right, you turn in 350 and it's saying 2.
If you're down here and you have 350, it will say 2 with a centered needle.
So I have now I have the idea. I'm flying towards that station.
Well, maybe not. You could be flying this way.
Oh, I see. Okay.
So now when you get that, if you want to fly to that station, what you need to do is turn to a heading of 350.
Oh, I see. Okay.
And, all right?
Well, it's something to help the navigation thought in mind.
Right.
Because I've always been following this.
Yeah. Well, you need to go out, and once you feel like you understand it here, and then the first time you go fly it, you're going to be befuddled again. Right, Tim? You got to go fly it a few times. And you go do it a few times, and I go, okay, well, this is starting to make sense now.
Well, I
Starting to
haven't
make
even seen
sense.
this thing yet.
Right.
But I want to be able to understand it.
Right. So from the standpoint of knowing where you're at, the easiest thing to do, if you want to know where you're at in relationship to a particular VOR, is let's say that, let me get rid of these radios. Let's say that's the VOR right there. And you tune in that VOR, okay? Then you just simply want to spin the OBS until you get a centered needle with a from indication. When you get a centered needle with a from indication, if it centers on 030, then you know that you are somewhere on this line right here, 030. You're somewhere on that line.
That helps a lot.
Yeah. You don't know where. I mean, you could be 20 miles out, or you could be 1 mile out, but you're on that line. Yeah. Because if you have a centered needle with a from indication, that is the radial, that is the spoke, that is the omni that you are physically located on. Doesn't mean that you're heading in that direction. Just means right now at this very second, that's where you are.
Yeah, let's say I'm flying perpendicular to that line you just drew.
Okay.
And I'm still watching this.
All right. So you're
that-
flying.
that
So let's say you're
needle
flying that way.
is going to start deviating.
Yep.
now, right?
It sure is. It's going to deviate. Which way is it going to deviate?
To the left.
No.
No, to the right.
To the right, because think about it. If what it thinks, if you get a from indication with a 330, what you need to put in your head, you need to think in your head, okay, well, I'm supposed to be flying like this from on 030. So if I go this way and I'm out here, now it's going to tell me that my course line, my course is over here, because I need to go to the right to get back to my course. But that doesn't make any sense unless either mentally or physically you turn the airplane in that direction. Now it makes sense. Hey, I got to fly to the needle to get back on course.
Now this.
Okay?
Now it's.
Good, good, good. All right, why don't we take a break, and I'm going to see if I can charge this. Tim, you had a further question on this?
Yes, sir. When tracking the VOR and say the needle deflected like that, which is 2, 4, 6.
Yeah, 6 degrees, yep.
And you told me before, that information's left my mind, to intercept where I want the actual course, when should I start turning?
Okay, I understand. I understand your question.
When you were working with me, I tended to overshoot.
Yeah, you would overshoot. Yep. All right. So Tim's question is, let's look at these. Let's look at the degrees off course here. So here's our center: 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Okay. Here's our VOR. All right. Let's just use this 180 radial because it's just easy to draw straight down. So in this case we have 180, or in this case we could have 360 with a 2 indication. That would give us a centered needle. That makes sense? So we have this VOR tuned in, and we have the OBS looking at this one right here. We have it looking at 360. We're down here, which means we're headed to 360. If you get a centered needle with a 2 indication, the radial you're on is the reciprocal of what's on the OBS. You're on the other side. The other thing you do is just spin it 180 degrees, and then you get a from indication with a center needle. But you can also stop it too and just do the math. You know, it's the other side of that. Okay. All right. So here's what this is showing. We're right on course, but we could also take the 178 radial, the 176, 174, 172, 17. Okay? If we were here with this setup, our needle would be right here. We're 2 degrees off. Okay? If we were here, our needle would be over here at 8 degrees off. So then we could do the same thing. We could look at this and know that, okay, well, that means we're on the 172. If we could do that math in our head, or we're at least, if we don't want to know what the number is, we know that we're 8 degrees off course. Okay? All right. So Tim's question was this. And here's what he was doing. Well, let's say that he's 8 degrees off. Let's say he's over here. Okay? And he's flying on a heading of 360. So he's headed in this direction right here. But his course line is to his left. What he was doing is he would make a turn like this. And then he would just rapidly blow right through his course line, boom, and be on the other side. Because his intercept angle was way too big. So his question is, how do I set up an intercept angle? So in order to set up an intercept angle, you really kind of have, it's helpful if you know, if you have some idea of how far away from the station you are. Okay? So by that, let me drill in here on a VOR station, and let's call that 2, 4, 6, 8, 10. That's obviously not correct, but you get the point. The closer I am, well, I guess I could have done it here. The closer I am to the station, if I'm 8 degrees off or 10 degrees off, I don't need to set up much of an intercept angle. I'm going to get there pretty quickly. But if I'm 50 miles out, if I only set up 1 or 2 degrees of intercept, I may never reach it by the time I get to the station. So the intercept angle has to be a little bit bigger angle. Does that kind of make sense? All right. So generally speaking, what I typically will do when I'm flying a VOR, if I know I'm real close, then I'm just going to set up a small, 5 degrees or whatever. If I know I'm a distance away, if I got a long ways to go, I got 8 or 10 degrees to go, and I'm a ways away from the station, I might set up 20 or 30 degrees of angular difference. So instead of flying 360, I might fly 330. And as I'm going this way, that needle starts coming in and in and in and in and in and in, and when it centers, I just get back on course. But if I'm doing this, I'm going to fly through it, and now I'm going to be doing this, and I'm just going to be S-turning through it, and I'm never going to I'll never intercept it because I have such a steep angle going into it. So just set up a shallower angle as that needle comes in, get onto the course.
You're watching it as you're.
Yeah, you're seeing this move. As you approach, this moves in and in and in and in. Yeah, so that's what you're asking, right? It's all about the intercept angle that I set up. If I want to intercept this course right here, you know, I'm flying this way, and maybe I turn 10 or 15 degrees, and I intercept it right here. But if I turn 90 degrees, boom, I'm going to blow right through it, and then I have to turn around and blow right through it. And you see, so it's the angle of intercept that you set up.
I mean, if you're ever gonna be using something like that, you're gonna have a general idea of maybe where you are.
You're going to have, yeah, you're going to have some idea where you are, sure. If you're using, if you're using VORs, and I used to know it. It's a rule of 60. There's a way to figure out how far away from the station you are. I just stumped myself because I don't remember it. We used to have to use this. It's the rule of 60. It's basically turning 90 degrees from your course and timing the time it takes to go through 1 degree. And then there's a formula that then you can calculate using trigonometry how far from the station you are. I just don't remember what it is because we just don't use it anymore. It's a trigonometry problem, yeah.
So just for additional context, the VOR system, so like, I read that some airports are not repairing or fixing
That's
the
correct.
VORs
Yeah.
that go out, so once they go out, it's over. Is this a US thing, or was this like, if you're flying a small aircraft in extra, like, is this how
They
you-
could have VORs, sure.
So everywhere that basically has some form of radio communication, likely at one point had a VOR.
Yeah,
Okay, so now that they're not replacing them,
Mhm.
what is the next intent?
GPS.
Okay, that's.
Everything is GPS. Everything's going GPS.
Okay.
Yeah, yeah. Started with bonfires. You'd fly from bonfire to bonfire to bonfire. You know, in the mail back in the 1920s when the airmail service. At night they would go bonfire to bonfire to bonfire, and during the day you would have routes where they would have beacons, and then as you approach the station, they'd have these big giant yellow arrows painted on, or not painted, but concrete painted yellow, and you okay, now go that way, and then you see the big arrow, now go that way, now go that way, and then they came up with radio ranges where you'd fly from station to station, and you'd have a range. Let's say you have a station here and a station here, and you want to be on that course right there. But this station here, and I don't remember the frequency, but from here it might be sending out a signal, Morse code signal. On this side, the Morse code signal was dash, dash, and on this side it was bump, bump. Right? So as you fly along, you wear your headsets, and if you're hearing bump, bump, you fly this way until you hear bump. If you're too far this way, you hear bump, bump, bump. You fly back this way to hear and you would just fly along the radio range until you got a solid signal. Then they came out with ADF, and ADF was the precursor to the VOR, and there's still some ADF. There's still some ADFs around.
That's
Automatic direction finder. Yep, it's an AM frequency. And when I started flying back in the late 70s, we used ADFs a lot, but we also used them to listen to AM radio because there were three. You'd listen to the radio station while you're flying. That's how you get radio. You'd listen to baseball games or whatever while you're flying on the ADF. But those were automatic direction finders. But all they did is they sent out just an omni signal that went all directions. So you could tune into that, and you had a needle kind of like this, with a needle that spun around, and you could fly. You know, let's say you were here, all right, and you're pointed to the station. You tune in the station, and you get that needle to point straight up on the nose, right? If you keep the needle straight up on the nose, you fly directly to the station if there's no wind. If the wind was blowing like this, then you would still get to the station, but you would do it like this. So you had to use some math, but if the wind's blowing like that, you'd still get to the station, but you'd get there like this. If you kept the needle pointed straight up, because the wind is going to blow you this way, and then you know you're keeping turning the airplane to keep the needle pointed straight up, and you end up approaching the station like that. So you'd have to use, again, I don't remember, there's relative bearing minus relative bearing. You have to do some math in your head to figure it out. Well, how much do I got to cock that needle sideways to make this stay on course? You had to figure out what the wind correction angle was going to be to stay on the course to the station.
And you just follow that heading.
And then you just follow that heading, yeah. And these things, I mean, I used to know how to do it. I haven't done it in so long, I don't remember the math involved in it. But, and then VOR took over from this, and now GPS. So that's the history of radio navigation thus far. All right.
But they still ask those questions.
They don't. You're not going to get any ADF questions.
You don't think so?
No, I know you're not. You're not going to get any ADF. You might get. You may VR. Well, you won't get any VR questions because you're doing sport. You talking about on a written test?
Right,
You won't get
right.
anything on the written test because you're doing
Oh,
sport.
really?
Nope. No written test questions on it. Okay. Anything else on this stuff? All right. What's next?
I have one about
Inspections. Okay.
So, for the inspections that are on,
Okay.
is it depending on what an airplane is used for, or if it's not
Yes.
IMC?
It's depending on what it's being used for. Oh.
So like,
Well, yeah, so, okay, so the question, that's a good question because we were just talking about this yesterday. Let's bring the inspections up first of all. So, what's the acronym for inspections? Aviate. Okay. Annual, VOR, 100 hour, altimeter, transponder, ELT. Okay, so there's your inspections. These are inspections that refer to Part 91 operations, only Part 91. This isn't Part 135 or 121, this is Part 91 operations, so the stuff that we're doing. Okay, of these inspections, if you're operating an airplane under Part 91, there are 2 of these that are always going to get done. What are those 2?
Annual 100 hour.
Nope. Annual and ELT. Those 2 are always going to get done. If you own your own airplane,
Was that 100 or?
100 hour inspection. 100 hour, yeah. 100 hour inspection. Okay, if you own your own airplane, you got to do an annual every 12 calendar months, and you got to do an ELT inspection every 12 calendar months. So you usually do them at the same time. Okay. So those are getting done all the time under Part 91. VOR inspection is only required, and this is the question you're getting to, for IFR operations.
Only for
Right. Only for IFR operations, and it's every 30 days. And this is an inspection that the pilot can do. You can do this either on the ground, where you're testing the accuracy of your VOR, or in the air, where you have a little more leeway.
So IFR operations, that's if the aircraft is
Capable and is being used.
is being used.
It can be capable, but you're not flying at IFR, then, and if you don't have a VOR inspection within the last 30 days and you're just flying VFR, it doesn't matter.
Okay.
Yeah. Okay. All right. 100 hour. Well, let me answer her question. Altimeter is also IFR, and transponder is where applicable. So typically we think about airspaces or where are we at in the atmosphere that we need a transponder. Okay. 100 hour is, we generally just think of if it's going to be rental, if it's a rental aircraft, it needs 100 hour. If you're using it for flight instruction or you're renting it out, you need a 100 hour inspection on it. Okay. All right. So your question is with respect to this one, right? Specifically, because this is the only one that's, well, that one's IFR too, but So your question is, if you have an airplane that is IFR equipped, and when does the altimeter inspection have to have been done? Well, this is 24 months, but if you're flying on an IFR, if you're flying under the hood, but you're not in IMC, do you need to have an altimeter inspection?
Yeah,
No, you don't.
okay.
If you're just flying under the hood. But is that your question, or is your question if you're on an IFR flight plan, even though you're in IFR conditions? I mean, VFR conditions.
I was also on
Okay, so that's one that we grappled with yesterday at the instructor meeting. And I'm not sure, I'm gonna tell you where I think I fall on it. Let's go to the extreme. If you're flying on an IFR flight plan and you're in IMC conditions, you absolutely have to have a 24-month altimeter inspection in the logbooks. You have to comply. If you're flying on an IFR flight plan, this is where the question that we grappled with. If you're on an IFR flight plan, but it's VMC, so you're on an IFR flight plan, but it's beautiful weather. You can see outside the airplane, but you're on an IFR flight plan. Does that 24-month inspection have to have been done? And I say the answer is yes, because you're on an IFR flight plan, therefore your altitudes had better be correct. The system needs to have been inspected and tested so that you know you are within the standards to be flying in the IFR system, regardless of whether it's IMC or VMC. That makes sense? So logically, and I haven't gone to look at it, but I think logically that's the answer, is yes, it needs to be done.
And then the same for the VOR.
Well, the VOR just has to be done within the last 30 days, but yes, and the answer is yes, but you can do that while you're flying. All you need to do to test the VOR is if you're on the ground and you're at a location where you can get a VOR signal on the ground, you need to be within 4 degrees. If you're in the air, you need to be within 6 degrees. It needs to be accurate within 6 degrees. And then you record that in usually a logbook that you just keep in the airplane. That just needs to be, and any pilot flying that airplane can do the VOR check. It's called a VOR check. It's got to be done every 30 days. So that's a no-brainer. This you're not going to find this one in the logbook. You're going to find this one in the airplane, typically. Okay, and then transponder. When do we have to have a transponder inspection done?
24 months.
It's every 24. So this is 12 month, 100 TAC hours. Okay, 30 days, 24 calendar months. Okay, transponder needs to have been tested and inspected within the past 24 calendar months if you're flying the airplane in well, IFR conditions in this case too, because you want to make sure that's working. But if you're VFR, if we're VFR, which we are, we have to have transponder tested and inspected within 24 calendar months if you're going to be flying in airspace that requires it. So what requires, and I say transponder, when I say transponder, I want you to think mode C transponder, not just it needs to be an altitude, we're talking about an altitude encoding transponder, not just a transponder. All right, so where does that need to be? What airspaces require an altitude? B, C, and?
It's also like outside of the border of the United States, and then 10 other miles around this.
Okay, and where else?
D.
Where?
That's D.
D, no, not in D.
Within the mode C.
Within the mode C veil, yep.
Alphas, right?
What's that?
Alphas as well, yeah.
Alpha, yes, but there's something else specifically I'm looking for. Above 10,000 feet. Everything above 10, which includes alpha. Everything above 10,000 feet requires a trans. So the easy, quick way to think about it is B, C, and above 10,000 feet. Okay? But when you think about B and C, as well as within the mode C veil, okay? And then you need to think about below and above. So even if you're flying, here's the ground. Let's say this is a Charlie airspace, which goes up how high above the ground? Typically. No, not a Charlie. How high does a Charlie go?
5,000.
Almost.
4,000.
4,000.
That's Charlie?
Yep, 4,000 feet AGL. Okay. And the mode C requirements up here at 10,000 feet. Everything up here requires mode C. But if you're in a Charlie airspace, you need that mode C not only in it, but down here below it, as well as above it, up to 10,000 feet. So in that whole cylinder.
Question.
Yeah.
Let's say I'm flying and see my daughter,
Yeah,
you know, one at a time.
yeah,
And I'm flying above Charlie airspace.
yeah, up here somewhere.
Yeah,
You-
I have to have that thing.
You gotta have your mode C. If you're gonna fly above it,
Even though I don't have to necessarily call them.
yeah, you don't have to be talking to them, but you have to have your mode C. Yep,
And we have that function.
yes. And and our transponders are tested. We don't do the altimeter inspection because we don't do IFR. We're gonna start doing it on the one plane.
Can you do IFR in this one?
We can now because we put an IFR certified GPS in 406. So as I actually went online yesterday, so as of today, we now start doing IFR training. Yeah, today in that airplane. Yeah. So that one we'll do an altimeter inspection on. We do transponder in all of them because otherwise you'd be restricted on where you could fly the airplane. We don't want the restriction. You can fly, you know, where you want. Okay. Good. All right. What else? Did that answer your question?
Yeah.
Good. All right. Any other questions on inspections? Inspections is one of the things that goes into continued airworthiness. It's the I in DI, right? Documents, inspections, and equipment. So this is one of the three things that goes into continued airworthiness.
Where you don't have to have it if you're like.
Yes, if you're a flight training, yes, so a flight school, so if I could operate as a flight school, any one of my airplanes without the ELT, as long as, if I'm taking it out to send it out to get repaired or something like that, I can do that. I have to make a logbook entry, and I cannot fly that airplane more than 50 nautical miles from the airport. And then I could have it out legally and fly it in training. Yeah, but I've done it before, but it's not a normal occasion. And it's only you're allowed to do that only while you're getting it you're getting it repaired, essentially. Yeah. Okay, good. Keep them coming.
The heading indicator, that's a vacuum gyroscopic device.
It's not the heading. Well, depends. It's not vacuum. It's gyroscopic.
Gyroscopic, but doesn't it work off vacuum?
Yes, that's vacuum. Well, it depends. Ours is not.
Oh, ours is electrical.
Ours is electrical. Yeah.
Okay.
So it depends on the plane. So you need to be aware of do you have a vacuum system in your airplane? If the airplane has a vacuum system, you're only going to find that in airplanes that have analog type style gauges, the round gauges. Okay, but that doesn't mean that they're vacuum driven. It could mean that. They could also be electrically driven. Okay, but if you do have the analog gauges and it has a vacuum pump or a vacuum system, the vacuum system is driving the attitude indicator and the heading indicator. Yeah.
Now, there was something I was reading about, and I didn't understand this, that you have to, as you're doing a cross-country flight,
Uh-huh.
you may have to adjust the heading.
Yes. So if you have that's okay. That's a good question.
How does that?
Okay. So the issue is, let me grab something here.
I want to add one income to see if you pick up at work and then I can cut my Sundays out. I'm a Patriot fan, but we kind of not terrible right now.
Okay. So with a vacuum system, they're driving gyroscopic instruments. So a gyro is a spinning disc. All right, and so when you move that spinning disc, it will process. Okay, so as I'm spinning this, as I move it up and down, and I'll let you do this, you'll feel it. You'll feel it pulling. Yeah, just spin it and then just kind of move your wrist up and down. You feel it kind of turning in a weird. Okay, so that's precession, right? So inside the airplane, anybody else want to play with that? All right, inside the airplane, you've got that gyro spinning for your heading indicator, and that's what's keeping your compass card or keeping your Essentially what's happening is you have a compass card and your airplane, as you turn, that compass card is turning, and because of that gyro, that rigidity in space deal, and it's supposed to always tell you what your heading is, right? But every time you make a turn, or over time, it will begin to process. Every time you turn the airplane, it causes a little, what you were just feeling, it causes a little bit of that to happen with that spinning gyro. That causes the instrument to process. And it'll read a little bit off, a little bit off. So over time, and the way I used to do it is about every 10, 15 minutes, as long as I'm flying straight and level, I'd look at the magnetic compass and I would just simply reset the gyro. Just reset it to what the magnetic compass. And the more maneuvering, and if I'm doing a lot of maneuvering, I would go wings level more frequently and double check it and then just reset it. So when you're flying an airplane that has the gyros like that, when you start the airplane up, the vacuum pump gets going and it starts spinning up the gyros, okay? Well, you don't actually set your heading indicator or trust it until the gyros have been up and running and spinning long enough to get them going, right? Okay, so when you first start the airplane, your heading indicator may not match anything that the compass is, right? So you start the airplane, you get it running for a while, and then you look at the compass, you look at the heading indicator, and you adjust it to get it to the right place. I think I have an old heading indicator in here I can show you. I think I have one.
You adding any deviation to that? No, there's supposed to be.
No, there's a deviation. That's a compass deviation card. So here's a heading indicator. Okay, so you have a knob here where you can set it to what the magnetic compass is, because over time this deviates. That's all it is. If it's a vacuum driven instrument, some of them are electrical. If it's an electrical instrument, you don't have to worry about it. That help?
Yeah.
Okay.
Yeah, they do.
All right.
I'm just kind of curious about for like the approach speed,
Mm-hmm.
because I was wondering why the Remos is faster than like the 1.3.
Why it's faster than 1.3 VSO? Okay, so question is the approach speed in the Remos. So generally we take approach speed. A general formula for approach speed is 1.3 times VSO, which for us would be 45 times 1.3, which would equal what? Somebody do the math. It's about 60. It's around 60, isn't it? No. 60 indicated airspeed. Is that what you come up with? I think it's 59 something. Anyway, here's the problem. It has to do with the mass of the airplanes that we're flying. It has to do with the mass, okay? If you don't maintain energy in an airplane, what happens? Stall. You stall. We don't want to stall, right? We don't want to stall until when? Till we're touching down. Exactly right. As we're getting right over the runway, that's where we want to stall it, right on top, 6 inches on top of the asphalt. That's where we want to stall it. So we don't want to run out of energy too soon, okay? Well, the reason that this formula exists is, and you could use this. I use this sometimes when I'm flying. I'll use 60 when I'm coming into to land sometimes. But you have to be very careful with it, okay? Because you can quickly and easily bleed off airspeed if you're not maintaining consistent pitch to hold that, okay? If you're not checking your airspeed or you're not maintaining a pitch, proper pitch, what tends to happen is as you approach the runway, here's what I see most 90% of students that I've taught in 30 years. This is what happens. Way up here, we start pitching up. What's happening to my speed as I increase this angle of attack here by increasing the pitch? What's happening to airspeed? I'm losing my speed. All right, so if I start this at 60 and I start bleeding speed off here, and I'm 10 or 15 feet above the runway, you know, right at stall speed, that's a dangerous That's a very dangerous place to be. Okay. If I'm flying an airplane that has a little more mass, a little heavier airplane, and I'm using 1.3 times VSO, and I'm coming in here and I recognize, oh, I've really slowed down a little bit. I don't have a lot of potential, okay? I have a little bit of kinetic, not a lot of potential, but I have mass. All I've got to do is just relax a little bit. I can build some kinetic back up pretty quickly because of the mass of this airplane. These airplanes have no mass, no mass, okay? So once you lose the energy, the only way to get it back is to push the nose over. And if you're at 50 feet, you don't have enough room to do anything or add power, okay? So I simply fly arbitrarily increases the speed that I want you to fly your approach at to keep you in a safer place. That's the reason that I have you fly it at 70, okay? And not 1.3 times VSO, okay? The other way to think about it is if you think about, when you think about mass and the kinetic energy and what's happening with it, if you take a baseball and you take, let's say you take your arm and you can perfectly calibrate your arm, take a baseball and you release it right here with the, whatever force you use in your arm, and you release a baseball and think about how far it would go, okay? Now take a wiffle ball, do the same thing. Is it gonna go as far? No, because of the mass, right? You're gonna drop off. You lose energy really, really fast. So I have you maintain a little higher kinetic energy to make up the difference in the total mechanical energy that you're going to lose when you slow down arbitrarily. However, that being said, if you're rock solid on holding approach speed, you can bring this in at 60. You can do it all day long. I have no problem with that at all. Don't get slow. Okay? And if it's gusty, now this is where this other thing that we say as pilots, we say add half the gust factor. You've heard that before? Add half the gust factor. So if the winds are 10 gusting to 20, what's the gust factor?
Yeah.
10, so add half, so add 5. So if your approach speed is 60, you're going to approach at 65. Okay, so you're going to add half the gust. So if you're using 1.3 times VSO, you better be adding half the gust factor to your approach speed. Okay? I arbitrarily tell you to come in at 70, and therefore you don't have to worry about half the gust factor. You're already at and beyond. If the gust factor is such that you got to go more than 70, then there's too much gust. You shouldn't be flying these airplanes. You're well beyond what you should be flying in these airplanes. Does that make sense?
Yeah.
Okay. Now, the other reason that we can add 10 mile an hour to this speed and not float all the way down the runway is because of the wiffle ball versus the baseball. If I come in a heavy airplane and I arbitrarily add 10 knots to my approach speed, I'm going to round out and I'm going to float, and land halfway down the runway. So it's really important with your typical type aircraft that has some mass to it that you use the correct approach speed so that when you get down there and you round out, from that round out point, you're landing somewhere within 400 feet or so of that round out point, which is a normal landing. All right? If you add too much speed to your approach speed in your typical aircraft, you'll blow past that 400 feet and you'll end up way down the runway someplace. Our airplanes, as soon as we round out, we immediately start bleeding off energy, and we land. We may float for 2 or 3 seconds, and then we land. That make sense?
Yeah.
Okay. So if you get asked that, I don't know who you're doing your exam with, but if you get asked that question, can you defend it? Okay. That's the important thing. As long as you can defend it, you'll be good.
Okay.
All right. I will tell you that if you look at the GX manual, it increases the approach speed. G3 gives you that approach speed. GX gives you 70, gives you a higher approach speed. Because they recognize that 60 is too slow. It's too slow. All right. What else?
So you don't have like airworthiness directives or anything because we're not certificated aircraft?
You could still have airworthiness. You could still get airworthiness directives, but we don't. There are none on the Remos. You could still get them. The FAA could still issue them. As far as, do you agree with that, Sabs? The FAA could still issue ADs or ADs On a light sport,
issue ADs.
yeah, we don't have any.
Yeah, I would just argue that there's not enough overall total time in light sport aircraft for enough AD.
Well, and there hasn't been any big, usually, an AD is gonna come out when the FAA finds there's a problem. Something's going on with this type or style or appliance or something, and that's when an AD comes out.
5,000 Cessna 172s in the United States. There's only 200 Remos in the United States. So for something large to happen, it would take a lot more time with 200 Remoses to have something occur to issue a.
Gotcha.
Yeah.
That said, are there like major rules about light sport aircraft that you know about, like Bryson to kind of look into them? I've been too busy to get around to it.
Major rules, what do you mean, major?
For like light sport aircraft, experimental, and certificate aircraft, you said? Just in case, like I don't know about the ISS or an oral exam or something.
So you're asking about the difference between certificated versus light sport versus experimental?
Sure, yeah, that'd be.
Okay, so you have different ways that an airplane can be certificate. So when you get your airworthiness certificate, okay, every airplane's got to have an airworthiness certificate, and that certificate is issued it's issued based on how the plane was built, essentially. So if the plane is built under the FAR's Part 23, then it's going to have an airworthiness certificate that is white in color, and it would be a normal airworthiness certificate, okay? And with that, that'd be your Cessnas and your Pipers and whatnot, okay? Then you have experimental aircraft, which are built, if they're amateur built experimental, they're built in somebody's garage. Somebody builds it. That somebody becomes the manufacturer. And then those are issued an experimental airworthiness certificate, and they're pink in color. Okay? Then you can have light sport or special light sport aircraft, which are built by manufacturers, but built under a different set of rules. They're not built under FARs, they're built under an ASTM standard. And those have also a pink airworthiness certificate, and they say special airworthiness. It's a special certificate.
Is that more like parachute?
That's like ours, special light sport. Yeah, if it's not a normally certificated airplane, in other words, i.e. the FAR's Part 23, I believe it is, Part 23, then it's going to have, it could be experimental, amateur, it could be experimental, it could be amateur built experimental. So an example of experimental could be a T6 from World War II, World War II trainer. Those are experimental category aircraft now, but they weren't amateur built. So it's experimental, but not amateur. But my airplane, that Long Easy in the hangar, that's an amateur built experimental airplane. Has a pink certificate, built in a garage, that kind of stuff, all right? If it's a special light sport, SLSA, then it's built by a manufacturer under a set of rules, ASTM standards. To qualify as a light sport airplane doesn't mean it necessarily would have a pink certificate. It could be something like a Piper Cub, which was built in the 1940s, okay, or could have been built in the 1940s. It happens to fall under the regulatory rules of the definition of a light, currently, that's getting ready to change, but currently it falls under the definition of what is considered a light sport airplane. But it has a white certificate because it was built under FAR Part 23. Okay, so it's normally certificated, but it's still a light sport airplane versus a special light sport, which these are, which were built under a different standard.
So these
Okay.
are ASTM.
These are ASTM. So an SLSA, special light sport aircraft, will have been built under an ASTM standard, and it will have a pink airworthiness certificate. Okay? Now, when we move into the Mosaic stuff, which is coming up in October, now you're going to have a whole bunch of light sport airplanes that are normally certificated light sport airplanes, 172s, 182s. Those are all going to be light sport airplanes, but they will have a normal airworthiness certificate because they were built under Part 23, but they qualify as light sport so sport pilots can fly them. Yeah.
If I understand right, the way that mosaic is gonna work, and you're limited to, you know, the sport.
You can only take one passenger.
Huh?
You can only take one passenger.
One passenger.
Yeah.
And, can't fly faster than 250 knots.
No, well, you're not going to fly. You're not going to find anything. If it flies faster than 250 knots, it doesn't. It's not going to.
It's not something I could fly.
Well, it's not something that's going to meet the standards anyway, because if it's flying faster than 250 knots, mathematically it's going to be difficult to get that thing to stall slower than 59 clean. It'd be difficult if it's flying 250 knots, it's got a much faster stall speed than 59. And that, generally speaking, there's some, when you design an airplane, you what's called sizing. And you typically start with, you look at you start with what do you expect the gross weight to be. And then based on what you expect the gross weight to be, you can back into formulaically a stall speed. And so the way the mosaic is set up is they're saying, okay, well, if the airplane stalls clean at or below 59 knots, then it'll be considered a light sport. And if you do the math backwards, then that means that generally that's about 3,000 pounds of gross weight, roughly. So that's why there's no gross weight limitation on it. It's a stall speed limitation. But mathematically, that will work out to something around 3,000 pounds gross weight.
So if it stalls at, let's say it stalls at 60,
Then it's not a light sport.
then it's not licensed.
Right. Right, clean. Flaps up.
Right.
Yeah. Okay. What else? We got 10 minutes before the next break.
Okay. Stump the instructor.
Stump the instructor. That's it.
Okay, I've been married 40 years. And
That stumps me right there.
Okay. And I'm always having to say I'm sorry. And you tell me how to not always have to say sorry.
As it relates to flying? Wait, this is a flying question.
Oh, okay.
No, that's not stump me on any. It's just got to relate to flying.
Okay. Anyway.
Because it has to do with that. Then I don't know the answer.
Okay,
There is no answer.
to NAVLO. They, kind of, the remotes, we always, or when we work with you, it's been a calculated of 100.
Calibrated, you're talking about calibrated airspeed?
Yes.
Okay.
How do we've had a discussion before, and how do you defend that? How did we come up with that?
With the calibrated airspeed?
Yes, in the remotes.
Okay. All right, so calibrated airspeed is indicated airspeed corrected for instrument error and instrument and position error. Okay, so your indicated airspeed, so you always have to start with indicated airspeed. Your indicated airspeed is your your airspeed indicator is a pressure instrument. It's reading pressure. It's reading dynamic pressure. It is reading 1/2 rho velocity squared. That's what that is dynamic. This is dynamic equals dynamic pressure. Okay, so this part of this equation, or this of these parts of the formula, of the lift formula, this is the density of the air. That's the air density. And this is the true airspeed. Okay, so this is not indicated airspeed. This is not ground speed. This is not calibrated airspeed. This is the true airspeed, and it's the square of that true airspeed. Okay, these two components these two things multiplied together give you a dynamic pressure. So it's taking the ram air. Another way to think about this is the ram air pressure. This is what's coming in the pitot tube. Okay, and this is the density, or the spacing of the molecules, if you will, or excuse me, this is the static port, is what I want to say, static port. So what's the pressure at the static port, essentially? Huh? The barometric pressure. How much force, how much pressure is acting on the side of the airplane? Okay. And the lower in the atmosphere we are, the more that's going to be, the higher this is going to, the lower in the atmosphere we're going to be, the higher this will be, right? Make sense? Okay. And the higher we are, the lower that will be. The pressure drops as we go up. So think of this as the static port, if you will, and think of this as the pitot tube, if you will. Okay. So then you can understand why I put it in parentheses in the formula up here. When you do the lift formula, you don't have to have the parentheses there. I put it there because I want you to recognize that that is the dynamic pressure portion of the lift formula. That is your airspeed. Okay. So if we are flying such that the product of these two numbers is whatever dynamic pressure it is, it reads on the airspeed indicator in the form of miles per hour, knots, kilometers, whatever, however we want to set it up. Okay. Well, if it reads 100, well then that's our dynamic pressure speed is 100 miles per hour, knots, meters, inches, whatever you have your airspeed indicator set up to read. Okay. All right. In a perfect system, in a laboratory type system, let's say you could take your pitot-static system, which is what this is. Here's your static side, here's your pitot side. And you could have always the same indication. If you change the density and you change the speed of the air, the molecules going in the pitot tube, it should always read the same indicated airspeed, right? And this is your indicated airspeed. But we're out in the wild. We're flying an airplane out in the wild where that pitot tube doesn't stick straight into the airstream all the time, right? And so if I pitch the nose up like this and I fly at a high angle of attack, that air is not getting in there like it would if I was pointed straight into the airflow, right? So I have some error in the position of the pitot tube. Or I could be in a slip. Now I have error in the position of the pitot tube and error from a static port side. If I only have a static port on one side of the airplane and I'm slipping this way, it's going to read a little less. If I slip this way, it's going to read a little bit more. So I'm going to have errors, positional errors in the system. Make sense? Okay. So what a calibrated airspeed is the manufacturer builds the airplane, and they go out and flight test the airplane. And they say, okay, well, when I'm flying straight and level, I'm indicating 100. And they'll do it in different configurations, maybe flaps up, flaps at 10, flaps 20, 30, whatever. They'll do it in different configurations, and they'll chart this. They'll give you this information in the pilot operating handbook. And they say, okay, well, we're flying straight and level, and we're indicating 100, and now let's do some mathematical calculations to figure out what really is the airspeed, what it really should be, and that will be the calibrated speed. So if we're indicating 100, our calibrated speed is this. All right, well, now let's pitch the nose up here, and let's fly at this indicated airspeed and do those calculations again to figure out what is it calibrated to. And then they say, okay, well, if you're flying at 80, your calibrated speed is this. If you're flying at 70, your calibrated speed is this. If you're flying with 10 degrees of flaps at this speed, your calibrated speed is this, right? So they'll go through this litany of speeds and configurations, and they tell you in chart form or graph form, all right, if you're indicating this, this is the calibrated. So we have to go to something, a chart or a graph or something that the manufacturer has developed through flight testing and mathematical calculations that tells us, hey, if this is what's indicated, this is the calibrated number. Right? I didn't answer your question yet. I'm giving you the background to how we get to calibrated, okay? All right, so does everyone understand the difference between indicated and calibrated? Calibrated will be different, could be different than what you see on the airspeed indicator, could be different than what is reading on your airspeed indicator over here based on the position of the airplane and how the air is flowing into the pitot tube and around the static ports and stuff like that. You could have some positional errors that are going on. All right. The manufacturer will tell you, and they'll do that based on speed, not slipping. They're not going to slip and do stuff like that. That's based on speed. All right. That being understood, then we should all actually understand then that if I'm flying like this, I'm going to diverge a lot more off of, there's going to be a bigger difference between indicated and calibrated when I'm flying like this than when I'm flying like this. Does that make sense? Okay. So to defend it, is what you're asking, how did I come up with 100?
Yes.
Okay. The I don't think any of the Remoses have an airspeed calibration chart. So the manufacturer does not give us a chart which we can go to figure out what the calibrated airspeed is. The problem is, if you don't know calibrated airspeed, you cannot calculate true airspeed. So you have to have some calibrated airspeed to calculate a true airspeed. All right? So what I show you when we do the navigation class is that in the cruise portion of your flight, when you're cruising, whatever you're indicating is going to be so close to the calibrated number that we use indicated as calibrated. We use them as the same thing. We say that indicated airspeed equals calibrated airspeed in cruise flight, in a cruise condition. Not straight and level, because you could be flying straight and level like this, right? That's not cruise. In cruise. So when you're roughly, at a zero pitch or thereabouts, you're in your cruise configuration, such that pitot tube is pointed into the wind. Okay. Then calibrated and indicated and calibrated, we say are the same thing. So your question is, when we get to the navigation log in that box that says calibrated airspeed, how is it we end up always putting 100 in there? Okay. Well, when you're flying at cruise power setting, cruise pitch and power setting, which is zero pitch and about 5,000 RPM, what does your airspeed indicator read?
Somewhere around.
Right around 100.
98.
Because the answer would be to the examiner is I've flown this plane and I know.
Because I know that in cruise, I'm doing 100 knots. In this airplane, I don't have a calibration chart from the manufacturer, but I know that in cruise, at my cruise power settings, I indicate 100, and I know that I have very little instrument error, positional error, because my pitot tube is straight on. Therefore, I'm using 100 as my calibrated airspeed.
Okay, now my next would be, the top of climb we figured 65 knots calibrated. Is, what we've always written down, and 500 feet per minute climb. How did we come up with that? Is
All right, say that again, ask the question.
On our calibrated speed on our climb, we've had 65 knots and 500 feet per minute.
Okay, so on the
just
climb,
elaborate on
okay,
the
so on the climb portion,
Yeah.
we're at a higher angle of attack, right?
Right.
And I don't have a calibration chart to look at to figure out what my calibrated airspeed is. So I'm just using my indicator, I'm using what I would climb at, and I understand that there's a difference.
Okay.
There's a mistake in it.
And at that, we typically have a 500 foot per minute climb rate. Or is that-
Generally, yeah, I
Just
use about 500 feet per minute.
Try to defend.
And that's because I know that airplane, I get about 500 feet per minute on average in my climb. It's it's atmospheric
I
determined.
understand, but I'm
right?
just trying to defend.
Yep.
When I
Yep.
figure this, and I'm saying, well, Tim, how did you come up with it?
Right.
I don't say, well, that's because Dave told me.
No, you
I want-
don't need
you
to
know,
say because my instructor told me that. That's never the answer.
I know, but, so I'm trying to, that's where I'm going with this.
Yeah, yeah.
So, thank you.
Yep. All right, let's take another quick break on this thing back. I'm plugging in here. Died out on me pretty quick, so I'll talk loud towards the camera. What else? Got questions?
How do you recognize?
No, go ahead.
How do you recognize and avoid microbursts while flying?
Well, okay. How do you recognize that? Well, there's no real good way. I mean, if you see an intense rain shower or thunder, thing, you can anticipate potentially downburst or microburst. But they could occur. You don't have to necessarily. I mean, they could occur whether you have that going on or not. So, airports, bigger airports have a radar that pick that kind of stuff up, and they announce that stuff. But for us, not flying in those airports, are likely to have that kind of equipment.
I mean, it's possible you can run clear turbulence.
Oh, sure, yeah. clear air turbulence, so generally clear air turbulence is associated with the jet stream. That's where you get clear air turbulence. It's the stratosphere and the troposphere coming together, the tropopause. And so you have two very dissimilar air masses. So you know we talk about a front being two dissimilar air masses? Well, the stratosphere and troposphere are two very dissimilar air masses, and where they come together, there's a much turbulence. And that you can get a lot of clear air turbulence as a result of that. Usually when you hear clear air turbulence, and you hear airlines talk about clear air turbulence, it's that. That's what they're talking about.
I mean, I would say, how to avoid microbursts is don't fly around thunderstorms.
Yeah, stay away from stay away
I
from
mean,
thunderstorms.
but-
That's for sure.
Yeah.
But you could get, think about it, you could get severe downdrafts without a thunderstorm, right? What do you need for a thunderstorm? Well, if you have two of the ingredients but you don't have moisture, you could still have severe up and down drafts, which for our, maybe wouldn't be classified as a microburst, but for our airplanes, you could have, if you're close enough to the ground, and you have a downdraft of 2,000 feet per minute, can you outclimb that? No, that's pushing you into the ground. So call it a microburst, whatever you want to call it, it's still going to shove you into the ground.
Sure.
Yeah.
Would you be able to walk through, like fuel burn, like specifically in top of climb? Like what is how would you calculate that versus just straight level flight fuel burn?
So okay, so you need to get that from out of the operating handbook. So you can go to the operating handbook, you can go to the section 5, performance. And that will give you fuel burn. Fuel burn is directly related to what? Fuel burn, rate of burn, power output. So the further you have your foot pressing on the gas pedal, the more fuel you're burning over time, right? So your gallons per hour is going to be, on your climb, is going to be your max fuel burn. And you're going to get that out of the pilot operating handbook, out of section 5, typically out of the performance section. So it's going to tell you at full power, or at 5,300 in the road tax, 5,300 RPM, it's going to give you a fuel burn of, I don't know, I think it's like 6.5 gallons an hour or something like that.
That's full power.
At full power, yeah. And then it'll give you burn rates based on power setting. So if you're 5,000 RPM, I think the burn rate's 5.5. If you're 4,000, I forget what it is, but it'll give you different rates of fuel burn per hour based on your power setting. And then it's just a straightforward calculation from there.
Okay, so there wouldn't be any changes in a nav log calculating top of climb regardless, or
No,
depending
it'll
on
be-
atmosphere?
So it's going to depend on how you do this. All right, so let's draw so we take off, and the climb, and then the cruise, and then we descend. Okay? So we're going to have, one of these markers works good. Here we're going to assume this is a full power situation right here. And let's say that our book says we're burning 6.5 GPH right here, 6.5 gallons per hour for that period of time. And then we level off in cruise, and we use a power setting, or whatever cruise power setting you want to use. Okay, so you're in cruise here. We typically, for our airplanes, we're going to do it at 5,000 RPM. It's going to give us 5.5 gallons per hour. Okay, and then on the descent over here, on the descent, let's say in order to set up your descent at a 500 foot per minute descent, let's say you use an RPM setting of 35 or something like that. And let's say that gives us a burn rate of 3.0 gallons per hour. So now I know my burn rate, if I wanted to get this detailed with it, okay, which I don't always want to do, that will depend. But if I do want to get this detailed with it, then I need to calculate in my navigation log, need to be able to calculate this distance right here. So I need to know the distance, I need to know the time, which means I need to know the ground speed. Right? So I have to calculate that, and then So if I know the time times 6.5 gallons per hour, I know how much fuel I'm burning right there in that lake. Okay? Then, same thing here. I need to know what my ground speed is. I know what the distance is here pretty easily, so that I can calculate my time along this lake times 5.5 gallons per hour. I know what my total fuel burn is. And then I need to be able to calculate the same thing here. What is my time here? So it's a time function. You need to know what your time between your legs are from point to point, which is what we do in the nav log, right? We figure out how long it's going to take me to get from here to here. So if I know it's going to take me this amount of time from here to here, I can multiply that times 6.5 gallons per hour. This amount of time from here to here times 5.5 gallons per hour, and then time from here to here times 3 gallons per hour. And then I know my total fuel.
You don't need to necessarily get that detail.
I don't necessarily get that detail. Give me some examples. You're going to defend your.
What about rounding it out to like 6?
Okay, so you could round this to 6. You could round that to 7. Why would we do that?
To ensure you have enough fuel at your end.
Yeah.
Conservative. To make it conservative. Yeah, better than simple. We always want to err on the conservative side when it comes to fuel. But why would I want to get this detail?
If you have very little fuel and you have absolutely no choice.
Or you're going from here to here is at the edge of your total fuel capacity or close to your total fuel capacity. So if you're anticipating, so we have generally speaking, we say that we can fly these airplanes if we want to keep legal reserves about 3.5 hours. So I got about 3.5 hours to get on the ground. And that's a function of the usable fuel and the average burn rate and all that kind of stuff, right? So I know that on average,
And usable fuel is 21.
21.
In both the
Yep.
jets.
Yep. So I know that on average, I could go 3.5 hours. I know that in my mind, here's what I do. I get in the airplane and I look at the fuel, I look at the fuel sight gauge. Because that one never lies. Look at the fuel sight gauge. And if it says I have full fuel, I look at my watch. And I know that 4 hours from now, I'm going to be out of gas. Therefore, in 3.5 hours from now, my wheels are going to be on the ground someplace where gas pumps exist. That's the way I think about it. Just a simple way of thinking about it, okay? If my planned flight is taking me to here, which is well below the 3.5 hours, I'm not going to go crazy with all this stuff. I'm just going to look at my watch and know that in 3.5 hours from now, whatever time that is, I need to be on the ground. Okay, does that make sense?
Yes.
What I'm talking about? But if my planned flight actually takes me all the way over here, I'm going to be much more careful about how I do these calculations.
Yeah.
I'm talking about this from a practical standpoint. From a testing standpoint, you want to do it this way.
Right.
Okay, but from a practical standpoint, be conservative and think about what am I doing. If I got 4 hours of fuel, I have 3.5 hours of fuel on board, let's say, to the legal limit of a half-hour reserve during the day. I have 3.5 hours of fuel on board, and I know that in no wind, in this airplane, in no wind, that means I go 350 miles, I'm doing about 100 knots, right? 350 nautical miles. If my flight is 200 nautical miles away, and I'm not anticipating giant crazy winds, and I'm taking off with full fuel, I'm not really overly concerned about a fuel problem. I am looking at my watch and recognizing what time did I start the engine, and I write it down on my notepad. I started at this time. Therefore, right next to it, I'm going to say 3.5 hours later is this time. And at that time, my wheels are going to be on the ground, period. Right.
So at top of climb is when you successfully arrive.
You've
at
transitioned to your cruise altitude.
Cruise altitude.
Yeah.
The
Or-
descent begins.
Yes, at the point where you want to descend going in. So now here's how I do a descent. What I typically do is I will descend, I typically will try and use about a 500 foot per minute descent rate. All right? Along this cruise phase right here, I have, I better have a real good idea what my ground speed is at this point, right? So I know what my ground speed is here, essentially. I know what my ground speed is. So therefore, I'm going to know based on my altitude that I'm starting at, I'm gonna know when I need to start my descent if I'm using a 500 foot per minute descent. Does that make sense?
Yeah.
So I'm gonna get however far out it is, and at that point, let's say it's here, I'm gonna now just reduce power until it shows me a 500 foot per minute descent. I'm not changing my speed, because if I'm trimmed for this speed and I simply remove power, what's going to happen? I'm going to begin to descend at what speed? Same speed. So I'm just going to pull power to begin. I'm going to get my power set so it ends up at a 500 foot per minute descent. Okay? And so if I'm, let's say I'm 10,000 feet above the ground. Let's say I'm 10,000 feet above the ground. Okay? And I want to set it for a 500 foot per minute descent. How long is it going to take me to hit the ground? 20 minutes. And if I know my ground speed, I know how far back I need to start my descent. And that's what I do. And then I end up where I need to be at the right time. All right, good.
What are we talking about next week?
Next week is aerodynamics. Week one of the rotation.
In this,
Okay, have a good one.
if this was a remodel, in this scenario, could I use the 65 knots and 500 foot per minute climb?
Yeah.
I mean, it's just as a, big
Yeah,
picture.
just as a general.
Just a big picture. I know I'm not figuring ground speed, I'm just saying for that portion of it.
Yeah, as a general rule,
Yeah.
if you're using 65 or 70 for your calibrated on the climb,
Yeah.
and you're using about 500 feet per minute, you're going to be pretty
Okay.
close.
You know,
It's going to be close
Yes,
enough.
and then the rest, figure the ground speed.
Yeah.
Then the average between this altitude and that.
Yeah.
Okay, thank you, sir.
Then going through some questions, question cards.
Okay, all right.
So, can you explain the difference between asymmetrical and symmetrical airfoil?
Yes, sure can. Okay, let me grab that. Can you grab the microphone there?
Oh, this one.
See if it's done enough to make it through the thing. All right, so the question is the difference between an asymmetrical and symmetrical airfoil. Okay. So when you look at an airfoil, typically when we talk about airfoils, we're typically talking about an asymmetrical airfoil, or sometimes we call it a flat bottom airfoil. Even though they're usually not flat, there's some curvature to it, but it doesn't have the kind of curvature that the top side has. All right, so when we look at the definitions or the characteristics of an airfoil, we know that airfoils have trailing edges, airfoils have leading edges, which would be this tangent point, the tangent point of the leading edge arc right there. And if you draw an imaginary line between the trailing edge and the leading edge, you have what's called the chord line, right? And that's what we use to define angle of attack, relative wind versus chord line. Then we have another line, which is the camber line. And the camber line is a line that goes from the leading edge to the trailing edge, but it's not necessarily a straight line. What it is it's a line that is equidistant between the upper surface and the lower surface of the wing. So everywhere along the chord, the distance from here to here is the same as the distance from here to here. It's a line, an imaginary line that is equidistant everywhere along the chord of this airfoil. Okay. A symmetrical airfoil, if this is my chord line, that is also my camber line. So you have symmetry on either side. So the camber and the chord line are the same thing. You have symmetry on either side. Okay, so that's the difference between a symmetrical airfoil and a unsymmetrical airfoil, or a symmetrical airfoil and a flat bottom airfoil. So with the exception of aerobatic airplanes and perhaps some military style aircraft, even military style aircraft don't necessarily have this. Aerobatic airplanes have symmetrical airfoils. most all general aviation airplanes are going to have some form of an airfoil that looks like this. Okay. So the advantage of something like this is that even at, let's say, a zero angle of attack. So let's say that the airflow is flowing. This is my relative wind right here. There's my relative wind right there. Okay. Now let's say this one, here's my relative wind right here. Okay. With relative wind like that, is there any angle, is there an angle of attack? Or what would the angle of attack be in this case?
Zero.
Zero. What would the angle of attack be here? Zero. Okay. The difference now is that this is not producing lift. This is. So at a zero angle of attack, an unsymmetrical airfoil will still produce lift. A symmetrical airfoil will not produce lift. This will produce lift because you have this larger area up here that is choking off airflow to a larger extent than this area down here. They're both choking off airflow. So you're getting a ventura, you're getting a lowering of pressure on both sides, but you have more pressure decrease here than you have here, which is a net lifting force. Here, you have the exact same amount of pressure decrease above and below, which means this wing will begin to, there is no lifting happening. So the only way that you can produce lift with a symmetrical airfoil is to be at a positive angle of attack. With an unsymmetrical airfoil, you can be at zero, and as a matter of fact, you can be at negative angle of attack and still produce lift.
That's interesting.
Okay.
You know, the big World War II buff.
Yeah, well, these are all.
P-51 Mustang.
Well, no, P-51 is like this, but it's a laminar flow wing, and it's a laminar flow wing, so it looks.
It's still asymmetrical?
It's asymmetrical, but it looks kind of like that.
Yeah, the bump is further.
Yeah, yeah,
Okay.
yeah. So that's the difference between the airfoils, and between the airfoils, and if you look at a polar chart, when it's, a polar chart's just a polar coordinates, you know, a Cartesian chart. So when you look at a polar lift chart, typically you'll see lift, coefficient of lift, which is this right here, that number right there, your coefficient of lift, and then you'll have angle of attack down here, so AOA down here, and coefficient of lift there. And usually, if you have a flat bottom airfoil, what you're going to see is your coefficient of lift starts here somewhere, and as the angle of attack increases, the coefficient of lift increases up to till it falls off, and that's the stall, right? But what you see is that you actually end up with a negative AOA before you reach zero lift, because you have this hump up here. When you have a symmetrical airfoil, if you look at the polar chart, it starts right here. Because at zero angle of attack, there is no lift being generated. So if you look at a polar chart of an airfoil, you can immediately, by inspection, know whether it's symmetrical or unsymmetrical.
You ever flown an aerobatic plane?
Mm-hmm. The advantage of here's the advantage of something like this with an aerobatic airplane. Typically they're designed with a more of a mid stability, neutral kind of stability. So picture the angle of attack necessary to fly that Remos out there, right? So for straight and level flight, we're at a zero pitch attitude. The airfoil is probably something like that, right? And we're generating lift, right? And so think about the pitch attitude that we have to maintain. Think about the longitudinal axis of the airplane relative to the horizon, the pitch angle. Could we fly these airplanes upside down? We could, okay? But in order to if we did that, would the pitch need to be like that or more like that? It'd need to be more like that, because think about that upside down. Now I have to completely change the flow pattern around that wing. So to fly upside down, I got to fly like this. If I'm doing aerobatics in this kind of airplane, I'm flying like this when I'm upside down, and like that when I'm right side up. So as I'm rolling through rolls, I'm doing this as I'm rolling, right? With an aerobatic airplane, you just do this and it just does that. If you're flying straight and level like this, right side up, you flip it over, you fly just like that. Flip it over, you fly just like that. Flip it over, you fly just like that. So there's much less, it's not exactly like that, but there's much less of this having to happen because you have a symmetrical airfoil. Does that make sense? Now, we do have symmetrical airfoils on our general aviation airplanes. It's these back here. These are symmetrical. Typically, your elevator and your rudder, or excuse me, your horizontal stabilizer, elevator, and vertical stabilizer and rudder are symmetrical airfoils. We make them unsymmetrical when we move the movable part.
I thought they were kind of like asymmetrical, but they were like flipped upside down.
No, they're symmetrical. So it's going to look, your elevator will look, for your horizontal stabilizer, it looks something like that, and there's the elevator, or it could be a rudder looking straight down. So it becomes this when I deflect this down here. Now I have curvature.
Now, dihedral.
Dihedral.
The attachment of the wing to the plane.
So dihedral is, we use dihedral to keep, for stability. Lateral stability, roll stability. So if you have I'll draw two airplanes. I'll draw a high wing airplane, and I'll draw a low wing airplane. Okay? All right. Dihedral is simply the angle of if this is the wing, let's say there's the airplane. Dihedral is how much the wing angles up. What's that angle right there? Angles up. So when you look at this wing right here on this high wing airplane, this Cessna, is there any dihedral in that? Very, maybe a half a degree. It's a very tiny, tiny, tiny amount. But if you look at a low wing airplane, you see a noticeable dihedral, a noticeable amount of dihedral in a low wing airplane. This is for stability. So if we have a positively stable airplane, what we want out of positive stability, static and dynamic positive stability, is when we upset the airplane from a trimmed condition, pitch, roll, or yaw. In this case, we're talking about roll. We're talking about, when we talk dihedral, we're talking about roll stability, lateral stability. If we take the airplane and we bank it and then we let go, what happens? Does the plane want to right itself? If it wants to right itself, or if it does right itself, we have positive roll stability. We use dihedral to attain positive roll stability. Okay, so here's how we do it. In a high wing airplane, it's not as necessary. It's not as necessary because when I bank this airplane, all right, let me draw this a little better here. So I'll draw it a little out of proportion so you can understand it better. Where's my center of gravity? Right there. Where's my center of gravity? Right there. Okay, I'm banking this way, but the center of gravity always acts down straight towards the earth, right? So as that's acting there, it's righting, it's a pendulum effect, it's causing the airplane to right itself. Okay, what about this one? Let's bank this guy. What's that do? It makes it worse. It makes it worse. So the way we counteract that is we put dihedral on the wing. And now this, because of the way the aerodynamics is happening on these two wings, I'm generating a little more lift on this wing and it rights it. That's why you see dihedral on a low wing airplane or mid wing airplane sometimes as well. Mid wing airplanes can typically be a little more straight, and you'll see like no dihedral on an aerobatic airplane as an example, just straight out, because they want neutral stability. They don't want the airplane to right itself because they want to point the nose here or the wings there or the rudder there, and they want the airplane to stay where they put it. They don't want it coming back. We want it coming back, right? That's what we want. So that's the purpose for dihedral. You can have anhedral too. And another dihedral effect is swept wings. So you see the swept wings on airliners, all right? The reason you have swept wings is also roll stability. So as you end up flying faster, it does two things. As you approach Mach, it helps with airflow along the wing, but it also, in a turn, it also helps because of the sweep, helps right the wings. Yeah. So you'll typically see swept wings. The faster the airplane goes, you'll see swept wings for that reason too, for stability. All right, so there's dihedral for you. And on some fighters, you'll actually see fighters, you want fighters to be unstable, right? So on fighters, oftentimes you'll see anhedral. You'll see the wings droop. They want them to droop so that they are more unstable and then they're more maneuverable for that reason. Yep. All right. There's dihedral.
You know, we don't have not a thing on these planes, but I was reading about cow flaps.
Yeah, we don't have.
You always want to keep them open while climbing.
Yeah.
Descending.
Yeah.
But then you close them off to some degree. And
Yeah.
cruise.
Yeah, because you get otherwise you get cooling drag. Yeah, so cow flaps. So the purpose for cow flaps is that in a cow, typical cow. Okay. So you got your cylinders. Let's say you got a 6-cylinder engine. Okay, your airflow's coming in here, and it's flowing around the cylinders. And you got an air cooled situation, right? The airflow is cool. Typical aircraft engine. They aren't water cooled like ours are liquid. The heads are liquid cooled. But even ours, if you look at the bottom of the cowling on ours, you'll see a little lip that kind of does here. So here's the firewall. Firewall kind of comes like this and then goes back this way. And you'll see a place for air to escape. Well, it has to. Because if it can't escape, what's going to happen once this engine compartment pressurizes? Once it pressurizes, you have no more airflow. And now the engine quickly overheats.
Sure.
So you need air moving across those cylinders to take the heat off. So the way that happens is you have to have air's coming in, you got to have a place for it to get out. All right, well, what cow flaps do is it allows you to make that much bigger. And the more you open it up, the more air can flow through here for cooling. And when do you need that? You need that in high power situations on takeoff. So if you have an airplane like a 182, is a typical airplane that has cow flaps because it's got a big 235 horsepower engine in it, 6-cylinder, and you'll overheat pretty quick on takeoff. So you open those cow flaps for takeoff, and then but this is draggy. You got this flap hanging down. So once you get up at cruise where you don't need, you're backing the power off, you don't need as much airflow through here, you close those. Does that mean you're closing it off completely? No, there's still an opening. It's not as big of an opening. Right?
That makes sense.
Yeah, so you'll have these high power engines. You'll have cow flaps, high power engines. So that's what that does. Just gives it more airflow.
If nobody else has a question, I'm gonna
Keep going.
pitch you for mnemonics.
Say it again.
Mnemonics.
Mnemonics, okay.
Yeah, like you told me the other day about with the wind, if you're taxiing.
Okay,
into
turn
the wind,
into,
you turn into the wind,
dive away
and you
from.
dive away.
Yeah.
That's a great mnemonic. It
Yeah,
has-
right. Yeah, so crosswind taxi.
Fascinating mnemonics. I'm all yours.
Well, I mean, yeah, I probably got a bunch, but
Either love it.
I won't be able to rattle them off
Okay.
unless we're talking about that subject,
Okay.
right? But from a taxi standpoint, yeah, turn into, dive away from. Turn into, dive away from. And we use full deflection of the aileron. We turn fully into the wind direction. Why do we use full deflection? Because we don't know how much we need. So we use it all. Use all of it. We can't judge. The wing is not flying when we're taxiing, typically speaking, right? So we're going to use all of the deflection in case we get a gust and the wing all of a sudden does fly. We want the wing to be flying into the wind, not get picked up and blown over. So we want to be turned into the wind. If the wind's from behind us, we're going to dive away from the wind.
I have a question about the oil. So, well, first of all, what kind of oil do you use?
So we use a high gearing motor. It's a high gearing It's Mobile One is what we use, but it's really a motorcycle oil. It's for a high geared, high rev engine.
Okay.
Yeah.
And then if there's low oil, how much would you add at a time?
Okay. So you're going to add just, I won't add more than about 200 milliliters at a time.
Okay.
Yeah.
So if she's, let's say she checked the plane and the oil was just beyond that flat part.
Just a little below it.
Yeah, then you would add like
200 milliliters.
Check it again,
Yep.
make sure it gets them.
Yeah, get up on the flat. And how far up on the flat? So let's call this our, here's our little oil stick. Right? And we need the oil somewhere in this range right here, around that little flat part. Okay? You must burp it first. Everybody understand why you have to burp it? Does anybody not understand why we must burp the engine? Okay. You must burp the engine first and then see where the oil's at. Well, if the oil ends up, you know, let's say it ends up right here. Is that okay to fly? It is okay. Should you add oil? Maybe. What are some circumstances where you might want to add oil?
You might want to turn the engine a little bit more where you.
Well, let's say you say it was low, so you burp it. You do it a few times. You get it to burp 4 or 5 times. You want to make sure you get, and you end up here.
So you're flying across country.
You're flying. That's the answer. You're going to go along cross country. I'd add some oil to it. You're going to do pattern work. Fine. Fine. Down here, add oil. Make sense? And this oil up to here on the stick is equal to or less than 3 quarts. So this engine don't hold a lot of oil. So don't go put a quart of oil in it. I mean, if it's here, you don't put a quart in, you put 200 milliliters, 300 milliliters. Okay? Don't put a lot. If you do, if you overfill it, now the oil's up here, we need to drain some out. It's not that hard to do. Don't freak out over it. Just come get me or Sebastian. We've got to take the cowl off. There's a little plug on the bottom of the drain. You just unplug that, drain a little oil out, plug it back, put the plug back in.
There's also a entry point too, right?
A what?
An oil cap.
Yeah, there's an oil cap. Yeah, yeah,
We don't pour it down the same.
Yeah, you pour it
area
down-
of the stick.
yeah. You pour it down right down where the stick is at. Yep,
Okay.
you pour it right down there. Yep. Yep. The reason you don't want to fly with too much oil is because you end up with internal pressures in the crankcase that don't need to be there. Yeah. It's not the end of the world on a Rotax because we don't really have seals and gaskets like other engines have gaskets. You can actually blow gaskets out if the crankcase pressure is too high, you can blow those gaskets out. Yeah. Okay. Answered?
Yeah.
Okay.
What is mechanical turbulence?
Mechanical turbulence. We don't really get it around here too much. Mechanical turbulence is, let me think, what airports do we fly into that we get it? Kingsbury. Kingsbury, you could get mechanical turbulence. So mechanical turbulence is when you get down close to the ground and there are trees or buildings that are in the path that the wind is coming from. The wind hits those buildings or trees and it starts rolling off of that thing, whatever it is, trees or buildings, and now we have rolling wind coming through, and that's mechanical turbulence.
Sort of related to ground friction.
Well, it's stuff on the ground. So yeah, so let's say we're landing. Here's our runway. We're landing like this, okay. And over here you got a hangar building, right? And the wind's blowing this way. That wind's going to hit that building and just start being turbulent, coming over that building, and you're flying right through it. Where if the wind's coming from this side and there's nothing over here, there won't be mechanical turbulence until on the other side of the building.
You
Okay.
should just engineer everything to be aerodynamic, like even hangers.
Right? Yeah. Yeah. Yeah, so be aware of that. So if you're landing and when are you going to hit it? Right about round out. That's where you hit it. Right about the worst place to hit it. That's where you hit it. So how can you make yourself aware that you're likely to get it? Be aware of the wind direction, be aware of what's around the runway. And so if you know the wind's coming from over here and you're landing and there's buildings or a line of trees right there, you can expect, all right, I'm gonna be ready for some mechanical turbulence right at that roundout. That's when I'm gonna get it. Just be ready for it.
The question I'd like to ask, last time before, and do any one of them give you like pause and say like, oh, it's weather sketchy, or
No,
I just don't know a whole lot about it?
they don't get me pause. So so what causes fog?
They're being saturated.
Yeah, so we've reached condensation. We've reached temperature dew point. We've met temperature dew point. All right, so what are the five? So the name of the fog tells us how it forms. We have to understand that what's happening is we're getting our temperature and our dew point together, right? So what are the five kinds?
Slow.
Advection. Radiation.
Say?
Precipitation.
Precipitation fog, yeah. If we're using that one, precipitation, there's going to be two more there. There's going to be two more than this then.
And there's another one that's either up north or cold seas. Yeah.
Ice fog.
Ice fog.
And then there's one more. Steam. All right. Which one's the one that we always see? Everybody's familiar with this one. Which one? Radiation fog. This is one everybody's familiar with. So what's radiation fog? Where do you see it? When do you see it?
Often at night,
Early morning, in low-lying areas. On what kind of morning? Calm. Calm what? Cool. Calm, cool mornings. That's when you see it. So what's happening is, here's the Earth. Okay, and let's say during the day, let's say it's fall, springtime, right? So in the fall and the springtime, you have a bigger diurnal variation. Diurnal meaning the difference between the daytime temperature and the night, the hottest part of the day in a 24-hour period versus the coolest part of the day. And then that diurnal variation. So let's say during the day, the temperature of the air is 80 degrees Fahrenheit. Okay, so at the hottest part of the day, it's 80 degrees Fahrenheit, and let's say that the ground heats up to 80 degrees, 80 degrees Fahrenheit. So, okay. Well, what happens at night is, as the sun goes down, the ground begins to cool, right? Cool, cool, cool. When is it the coldest? When will the ground be the coldest? Just before the sun comes up, because the Earth has had as long a period of time to cool off. Okay, so now let's say that the temperature of the ground is 60 degrees. We drop 20 degrees. Okay, and let's say that the temperature dew point is 55, or let's say the temperature dew point is 65, something like that. Okay, so the temperature dew point, or the dew point, is 65 degrees. Well, the air right above the surface is going to cool down due to the cold radiating off the Earth, right? How does this temperature of the air out there over the pavement, how does it get its temperature? It doesn't get it from the sun. Sun heats the asphalt. The asphalt radiates it back up. So here we have 60-degree temperature air, and it radiates that air back up. And so the air, the temperature of the air right along this little layer close to the ground, let's say, is 60, right? Well, if the dew point is low, is 65, and let's say right up here, once we get this high off the ground, the temperature gets up to 66. Everything below 65 is going to turn into fog. It's going to condense. Okay, but that's going to happen typically on cool mornings. So usually around this part of the country, it's going to happen during the fall, winter, and spring. You see fog in the middle of August? No. Oh, because ground's hot and it stays hot. It stays hot. The variation, the diurnal variation between day and night. How hot's it get during the day? 100 degrees? How cool does it get at night? 90? Right? If you're lucky. So there's no big there's not a big diurnal variation. But in the wintertime or spring or fall, you can be 90 in the day and 60 at night. So it's when you have those big shifts. That's when you're likely to see fog, radiation fog formations. Okay, so that's radiation fog, all right? So it's easy, you can see that the ground is radiating that back up. Okay, all right? Let's look at upslope fog. Here's another one that's easy to figure out why it's happening. How does air temperature generally cool? What causes rising, right? So if you have wind moving air up a slope, what's the temperature of the air going to do as it goes up that slope? It's going to cool, and when it cools to the dew point, bing, you got fog. That's upslope fog. So you look up a mountain and you see these clouds, you know, at the mountain, right? So it looks like a cloud from where you're at, but when you're up on the mountain, that's upslope fog. You're in the cloud, you're in the fog. What is fog? Fog is a cloud that forms within 200 feet of the ground. That's fog. So it's a cloud, but it's just forming low to the ground. Okay, so that's upslope fog. All right, let's look at do this one last. Let's look at steam fog. So what is steam fog? Where is that going to develop? First of all, we know that it's a temperature dew point coming together. Okay, so just think, what is steam? Just if you had to define steam, where do you typically see steam in your kitchen?
Boiling water.
Over boiling water. So what do we have with boiling water? We have what?
Liquid.
We have a hot liquid that's rising up into colder air. So where are you likely to see steam fog? Hot water with colder air over the top of it. That's your steam fog. So you're going to see that in a situation where, again, it's going to be in these winter time frames, okay? And what is it about water that's, when we talk about energy and holding energy, how does water hold energy? Very well. It's like a battery. So if you have a swimming pool, I don't know if you got a swimming pool. If you got a swimming pool, where you're all familiar with swimming pools. As you come out of winter, that pool's pretty cold, right? And it stays cold for a while, even when the sun starts, but once it gets hot, once it finally heats up, it stays hot for a while, right? So as we go into fall and winter, and typically steam fog you're going to see in fall and winter, you won't necessarily see it in the spring because the water has already cooled down now. But in the springtime, or in the fall and in the winter, you can have a body of water. So let's put a body of water over here. Okay. So this body of water heated up to 80 degrees. This lake heated up to 80 degrees through the summertime. Got up to 80 degrees. And now winter comes along, fall comes along, winter comes along. And let's say at night, now it could be 90 degrees during the day, but at night, just because of the ground around it, the temperature of the air due to radiation cools down to 70. And we got temperature dew point thing happening right here. We got hotter water over colder air, and we get steam fog. That's steam fog. Anytime you think fog, it's temperature dew point meeting, right? Of what's causing it to meet. So there's steam fog. Now let's move to ice fog. What's ice fog? I've seen ice fog once in my life, and it was over Lake Michigan. And it was about negative, actual air temperature, about negative 30 degrees outside. And what it was is you had negative 30 with a 70 degree temperature lake. And we had steam fog that just turned to ice. So it was literal steam
Dangerous ice.
that was ice. It was just literally steam that froze in place. That's ice fog. Okay? All right. Advection fog. Where does advection fog occur?
Coming off ocean.
Coming off of oceans. Okay.
Onto the land.
Onto the land. Okay. Could go the other way too. Depends on whether you're having a sea breeze or a land breeze. But again, it's a matter of in the mornings or in the mornings or during the days, which direction is the wind typically flowing?
inland.
Inland, it's typically flowing inland. So in a situation where you have warm, moist air hitting the shoreline, which is cooler, okay, boom, advection fog occurs, all right? The opposite side of that would be in the evening where you have the flow coming this way and you have cooler air hitting warmer, moister water, boom, advection fog. So you can have it in both directions. It depends on which direction it's happening. But advection occurs when you have convection happening, sea breeze, land breeze, and you've got these moist things occurring. Okay? All right, based on that, what's precipitation fog?
Well, after rain, there's so much heat released from the
Yeah,
condensation.
that's what's happening. As the air temperature cools as a result of this, and you can reach condensation point. The act of the precipitation itself can cause cooling in the atmosphere, which causes precipitation fog. Does that make sense? Right? So if you think, all you really have to do is, all right, well, what is the name tells you how it's being formed. Fog is simply temperature dew point meeting close to the surface of the Earth. That's fog. What's causing the temperature dew point to meet? That's the definition of it. That's telling you what kind of fog it is. Okay? All right, we got 5 more minutes. One more question. These are great questions. I think the best questions we've had on the question and answer thing. Certainly very well varied, all over the place.
So that's what it's supposed to be about.
Yep, right, absolutely. Any more? Remember, I'm $75 an hour,
If nobody's
and I'm
gonna
free
ask,
right now.
You know, I would bet if I had the question in my mind, others would probably thought the same about the plane. Reply, hey, long downwinds and then long approaches.
Oh yeah, so
And the nature of why we do things differently. And I thought that was very interesting.
okay,
In
so
understanding
yeah,
our characteristics.
so the reason, so it's been there's been a shift over the 45 years that I've been in aviation. There's been a shift in the way pilots are trained. And it has been a shift from, in essence, training aviators. We used to train people to be aviators. Now we've begun to train people to be operators. And there's a psychological difference, a big important psychological difference between somebody being an aviator and somebody being a button pusher and an operator. And you do A, B, C, D, E, F, G, and if somebody pulls E out of the equation, you don't know what to do, right? So that's the big picture of what's happened. So, and it's been a slow, kind of insidious thing, and kind of the way it happened is you end up with a mindset. A lot of this is my opinion. You end up with a mindset of wanting to train everybody to be an airline pilot. All right. So there's nothing wrong with structure.
There's a big call.
There is a call, right? There's nothing wrong with structure. We have a lot of structure in our program, a lot of structure. But if all you do is think about structure, then the way that you teach is, okay, when you're here, you do this. When you're here, you do this. When you see this and this, you do this. When you see this and this, you do this. When you teach that way, you're teaching someone to turn knobs and push buttons, and you're teaching them to operate the aircraft, not aviate the aircraft, all right? When you teach someone to operate the you related it specifically to pattern work.
Right.
When you teach someone to operate the airplane, what you teach them typically, if it's a Skyhawk, is you teach them, okay, when you get to, and they don't even call it key position, which is another travesty, but when you get to the key position, what they'll say is beam the numbers, or, they won't use the term key position, so then that throws you off for other mental processes. But when you get to this point, relative to the runway, do this. Pull your power to this, reconfigure the airplane this way, fly until you're 45 degrees from that point back there, turn the airplane, reconfigure in this manner and repower to this configuration, or repower to here, reconfigure this way, turn it onto the final approach, reconfigure this way and put your power here and fly it and use power to fly down. That's operating the airplane, and that's the way they teach. Okay. Aviating the airplane is, if you're an aviator, then I can take an aviator and say, so here's the end of the runway. I can take an aviator and way back here, I can say, okay, I just pulled your power and you can fly that airplane right to that spot. Or I can say, just, okay, continue on down here, continue on down here. Okay, right here, I now chop the power here and you can make it to that spot because you know how to fly the airplane. You know how to aviate the airplane. When you get into a poor energy state, you recognize it before you're there. You recognize that you're getting into a poor energy state because you're thinking about aviating, not operating. Remember that flight that, I forget what kind, it was a, I don't know if it was China or what it was, but I think it was San Francisco, they ended up short of the runway.
Shorter runway.
Yeah, remember that?
Right, yeah.
That's a situation where you had 3 operators and no aviators. And they ran the plane out of energy and just hit before, they just did that and slammed into the ground before they hit the runway, right? Now, part of the reason for that is that there was some auto throttle things going on and the auto throttles weren't on, so power wasn't coming up. But all, if they were aviators, had to do is look out the window and recognize we're going short. We need power, right? But they didn't do that because they push buttons and turn knobs and expect the automation to save them, right? That's kind of just the difference psychologically between an operator and an aviator. And so when you see people flying these big, giant patterns, you know that they have been trained to be operators, not aviators.
That was very helpful.
Yeah, yeah, good. All right, good question. So next week we start back over in the first rotation of aerodynamics. So I think that's chapters 4 and 5. And then if you're part of Gold Seal, there are also some Gold Seal things that you can watch, some videos on there and some other parts of that to watch. All right.
Thank you.
See you next week. Yeah, you bet.